Welcome to ROS Crash Course 2025. Whether you are brand new to ROS or looking for a quick refresher, you are in the right place.
In this lesson, we'll guide you through the essentials of ROS, how it works, why it's so powerful for robotics, and how you can start building with it today.
And to make things easier, we'll be using the Construct, an online platform that lets you run ROS simulations and projects right from your browser. No need to worry about setting up your system. Just log in and start coding.
That means you'll get hands-on practice without the hassle of installations or dependencies. Just pure ROS learning made simple.
And for free, okay? Yeah. Then, no fluff. Just hands-on learning to get you up and running fast. So, let's dive in.
Let's dive in. All right, so this is the ROS project that we have prepared for this ROS2 Jazzy Crash Course 2025. Now, in order to open this project from your computers, all you have to do is to use the share link. We are going to be sharing this link in the video description for easy access. Now, once you use this share link, what is going to happen? Let me show you real quick. So, once you use this share link in your web browser, you are going to be redirected to the Construct login page. Then, in case you already have an account with the Construct, that's great. You can directly log in and you are going to be ready to start working on the project. In case you don't, you can either log in using your Facebook or Google accounts, or you can choose to create a new free account in just a few seconds here. In my case, I'm going to use mine here. So let me log in with my personal account. And once you log in, you are going to get a copy of this ROS project in your accounts. Now, the final step to complete is just to click on the Run button to start the ROS project. Now here you will have to wait for a few seconds until the full project finishes loading, and then you are going to be ready to start working on the course. There we go. So once the project finishes loading, you are going to see something like this. First of all, you will see a terminal which is automatically opened here. This is a regular Linux shell where some packages are being automatically installed. These are some dependencies that are needed for this specific project. And second, most important, is that you're also going to see the notebook for this ROS project. This is the notebook that we are going to be using for this ROS2 Jazzy Crash Course 2025, and where you are going to find all the theory, notes, examples, codes, etc. As you can see, you are going to find here the index, where we have a part 1 for ROS2 basic concepts, part 2 is ROS2 topics and multithreading, part 3 is for visualizing robot data with ROS2, part 4 is for robot frames and transformations in ROS2, and we have a final part for an introduction to DDS, data distribution systems. All right, so we should start from the very beginning, right? From the ROS2 basic concept, so that we can build the foundations for introducing later more advanced topics. And then, in order to access these ROS2 basic concepts part 1, all you have to do is to click here in the link provided in the index, and this is going to open the specific notebook for this part 1, ROS2 basic concepts. All right? Then let's get started, right? So let me close here or minimize it. Then the very first thing that you need to do is to start a simulation, okay? We at the Construct believe that the best way to teach is by doing, by practicing, yeah? Then everything that we are going to be teaching, everything that you are going to be learning in this crash course, you are going to be applying it directly to a real simulation here. Here we have a simulation of an office. Actually, this is the environment from the Office series. All right. And here you can see the robot that we are going to be using, which is a ROS2 Excel. Now, in order to start the simulation, it's very easy. All you have to do is to follow the steps here in the notebook, how to launch the simulation. And in this case, you have to execute these two commands here. Okay. Then let me copy them directly here from the notebook and paste them into the terminal. By the way, this terminal has been automatically opened, but in case that you want to open a new terminal, it's very simple. All you have to do is to click on the first button that appears here in the bottom menu, yeah, which says Web Shell. You click here, this is going to open a new terminal, yeah? And here then I can paste the commands to start the simulation. There we go. And then after some seconds, you are going to see that a gazebo window automatically pops up. Let me maximize it. And here you are going to be able to see the simulation. All right, let me maximize it and also zoom a little bit here to the robot to have a closer look. There we are. Okay, excellent. Then with the simulation started, we are ready to go with the course, with this first part, ROS2 basic concepts. Then what is ROS2? This is the big question, right? But before going to try to answer this question, let's first introduce some concepts. And the very first thing that I would like to do is to practice a little bit with ROS2, see what ROS2 can do. And for that, we are going to start by moving a robot, this robot that we have here in our simulation, using ROS2. Then for this, you have, again, a couple of commands here in example 1.1 that you can directly copy and paste here into the terminal, but not in this one, okay? Here in this terminal, we have the simulation running, so we don't want to close it or do anything else here. Otherwise, the simulation is going to stop. Then what we have to do is to just open a second terminal, yeah? Very easy, just click here in this Add button to create a new terminal. And this way we have a second terminal, new, which we can start executing new commands. In this case, we have the source again, which you can think of it as, let's say, starting the ROS2 system, yeah, by sourcing here in this case this specific ROS2 workspace. We are enabling the terminal to use ROS2 commands. And here we are using this specific command, which we are going to review in a moment. But basically what we are doing here is to start a ROS2 program that is going to allow us to control, to move this robot using the keyboard, okay? So let me press enter here to execute the command. And then you are going to see some instructions here, yeah, with the specific keys to use. For example, the I key is going to make the robot move forward. The K key is going to make the robot stop. Comma is going to make the robot move backward. And U, J, M are for rotating and turning left. And O, L, and dot are for rotating and turning right, okay? Then let's start this. So let me move the simulation here so that we can properly see it. There we go. And then here with the focus in the terminal, I'm going to start pressing the I key, which should make the robot start moving forward, right? Let's see. There we go. We can see how the robot starts moving forward. Now I'm going to stop it, pressing the K key. With the comma, I'm going to be able to make it move backwards. There we go. And also I can make it rotate to the left, for example, or to the right. There we go. Okay. So all these, I am doing it by using this ROS2 program that I have just started. All right. Okay. Then let's continue a bit more here. So what have we done here? Here we have started a ROS2 program by running this command here, ROS2 run, and then we have to specify two things. First, the package name, the package that contains the ROS2 program, and second, the executable file of the program, yeah? So knowing this structure, we can see that this command basically says ROS2 run, teleop twist keyboard. So this is the name of the package which contains the program, and teleop twist keyboard, this is the name of the executable where we have our ROS2 program compiled to, okay? These are some remapping commands, but we are not going to cover right now, okay? Then this is one of the ways of starting a ROS2 program, ROS2 run, directly to start a ROS2 program. There is a second method also to start ROS2 programs, which is using the ROS2 launch commands, yeah? In this case, again, we have to specify the package name, and then instead of specifying the executable file, what we specify is a launch file. Yeah? Again, this launch file has to be, of course, inside this package name. Okay? Now we are introducing some concepts here, like for example, package name, executable file, launch file. Then let's go by parts. So first of all, what is a package? Basically, a package is what ROS2 uses to organize its programs. Yeah? So you can think of a package as all the files that a specific ROS2 program contains. Yeah? Whenever you start working on a new program for ROS2, you are going to always start by creating a new package which is going to store all the files for that specific program. Yeah? Then here we are going to look at the typical structure of a ROS2 package, in this case, a Python package, okay? For ROS2, there are a couple of methods to create packages. Actually, there are more, but the two main ones are Python packages and CMake packages, okay? For the means of this course, we are going to focus on Python packages, and this is the structure of how a ROS2 package looks, yeah? You are going to have a package XML, which contains some meta information about the package, a setup.py, which is a file that we are going to use to specify how to build this package, okay? Here, we also have a setup.sfg, which defines where the scripts will be installed inside the package. And finally, we have a directory, which has the same name of the package, where we are going to put all the Python scripts that we create, okay? It also contains an init.py file. Now, this might be a bit abstract right now, okay? So for now, just get these concepts, yeah? So every ROS2 program that you want to execute is inside a package. Every ROS2 program that you create must be placed, organized inside a package, yeah? And packages are the primary organization system for ROS2 programs, yeah? But enough talking, let's get already to the practice, and for that, what we are going to do is to start by creating a new ROS2 package, okay? Then, for that, we need to know a couple of things. First of all, packages are always going to be inside a ROS2 workspace, okay? In our case, we have a workspace here, already created for you, which is named ROS2 workspace. This is a typical name for a ROS2 workspace, which is ROS2 underscore and WS, which goes for workspace, okay? Then, besides this, every workspace is going to have a folder which is named src, okay? Then all the packages are going to be placed always inside this src folder, okay? Then let's show this in our specific project. Then let me come here, I'm going to stop the program, and then I'm going to see first of all where I am located with pwd. So right now I am in home user, okay? So if you execute ls, you are going to see that here you have some different workspaces, right? The sim workspace is the one that we have been sourcing and using for launching the simulation, okay? Now we are going to work in another workspace for creating our packages, which is this ROS2 workspace, okay? Then let's get inside this ROS2 workspace. And again, you are going to see here some folders like build, install, log. All this is automatically generated when you compile the package, which is the next step that we are going to be seeing. And here you can see the src folder, all right? Now, before moving forward, I want to introduce another thing for this project, which is the code editor. Yeah, you can, of course, work using only the shell, but usually when you start working with packages, files, etc., you want to have some kind of graphical code editor, right? So you have this in this project, and in order to open it, all you have to do is to click on this button here next to the web shell button, which says code editor. Okay, this is going to open the code editor. You can see it here, which of course is going to show you and give you access to all these workspaces, but using a graphical interface, which usually it's much more convenient when developing, right? Then here we can see the ROS2 workspace with the SRC folder that we can see right now it's empty, right? So if I go inside the SRC folder, I can see that it's empty. And let me show again the path. It's the workspace, ROS2 workspace in this case, and SRC folder, yeah? So always, always, always that you want to create a new ROS2 package, you have to do it inside the source folder of a ROS2 workspace, okay? Let's continue. Then once we are in the proper directory, we are ready to execute the command to create a new package, and here you have that command, yeah? So let me copy it from the notebook, paste it here to the terminal. Here we go, yeah? And the command, you can see it's ROS2 package create and some things that we are going to review in a moment, okay? So first of all, let me execute this package, this command, sorry. And then now if I press ls again, you can see that we have a new package here named my package. Also, you are going to be able to see it here in the code editor, right? And you can see it has some of the elements that we have described earlier, yeah? You can see it contains here a package XML, a setup.sfg, setup.py, yeah? And also a folder here with the same name of my package, okay? It has some additional things, but these ones are the main ones, all right? Okay, then let's go back. So what does this package mean? Well, this package means ROS2, actually. Here we are missing a 2. Yeah, ROS2 package create, then you specify the package name. Yeah, so in our case, the package name, well, we are specifying it here. It doesn't matter, you can put it here, earlier, it doesn't matter, yeah. This is the package name, which is my package. Then we have the build type, okay. Yeah. This specifies which type of ROS2 package you are creating, yeah? Are you creating a Python package? Are you creating a CMake package? In this case, we say amend Python because we are creating a Python package, yeah? And then finally, we have the dependencies, yeah? So with this dependency stack, what we specify are the dependencies for my package. So other packages that my package is going to be using. In our case, we have one single dependency, which is rcl-py. This is the client, the ROS2 client library for Python, which basically allows you to create ROS2 Python-based programs, okay? All right, so we have created our new package. As I was mentioning here, there is other types of packages, especially the other most common one are CMake packages, where instead of amend Python, you would specify something like it is amend CMake. Okay. In any case, we are not going to cover all this. If you are interested in that, we have a course at the Construct, which is ROS2 Basics in 5 days, but in C++, where we cover these CMake packages, yeah, which are the main ones for creating code in C++, okay? For this course, we are going to be working with Python. All right, then here you have the basic structure of a ROS2 workspace. So you would have the ROS2 workspace with the SRC folder, and inside the SRC folder, you can have one or as many packages as you want inside. Yeah? Okay. Next step, we have created our package. So before being able to use a package or the programs that we create inside a package, we need to compile it or build it, yeah, which is the same. Then the command to compile or build a ROS2 package is this one, colcon build. Okay? Now, you might be thinking, okay, so then all I have to do is to type colcon build here, right? No, okay? In the same way as for creating a package, you have to be in a specific directory, which is the source folder of the ROS2 workspace. When building a package, you need to be in the root of the workspace. Yeah? So not in the src folder, but in the root of the workspace, here. Okay? Always that you want to compile one workspace or one specific package, you need to be in the root of the workspace, here. All right? Now here, you can press colcon build. You can execute the colcon build command, and the packages inside your workspace are going to be compiled or built. Yeah? In this case, we only have one package, which is my package. So this one is the one that is compiled. Okay? Now, there is the possibility to compile one specific package, yeah, because as we mentioned earlier, inside the ROS2 workspace, you can have as many packages as you want, yeah? Then maybe in some cases, if you have many packages, but you are only working with one specific package inside your workspace, it might not be worth to run the colcon build command, because you are going to be building many packages that you are not updating or working with, right, which is going to take time. In that case, what you can use is the packages select, yeah, to specify which package or which packages, specific packages you want to compile, right? So if we add this to the colcon build command, like this, not this, sorry, let me type it. So it's colcon build -- packages select, and then the name of the package that you want to specifically compile. Yeah? Okay. Now, we have already introduced the concept of package, but what about launch files? Yeah? So we also introduced here in the first example the concept of launch files, which is another way of launching ROS2 programs. Yeah? So what is a launch file? Well, a launch file is a way of launching ROS2 programs in a more organized way. Yeah? And it's the usual way in which ROS2 programs, at least the more advanced ones or complex ones, are launched. Yeah? Why? Well, because the ROS2 run command, which is the first one that we used here, allows you to execute, to start one ROS2 program. Yeah? Using launch files, you can launch and start at the same time many ROS2 programs, okay? As well as doing several other operations that are not possible with the ROS2 run program, okay? Then, how to create a launch file? Well, it is something like this. In ROS2, the most common way of creating launch files, let's say, is using a Python script, okay? And the script is going to look something like this, okay? So you need to import some things here that you need for launching the ROS program, and then basically what you are going to do is something like this, yeah? Using the node class here from launch ROS actions, you are going to specify the package, so the name of the package which contains the ROS2 program that you want to launch, and then the name of the executable, you specify it like this. Yeah? Then you have other options that you can specify additionally in a launch file, like for example output. Yeah? This sets where the output of this program is going to be sent to. In this case, for example, if we set screen, this means that the output of this program is going to be seen from the terminal. Okay, but maybe you can redirect the output of the program to a log file or things like this. Okay? Then this is the basic structure of a basic launch file. Of course, you can create more node elements with which contain or start other ROS2 programs. Okay, but for now, let's keep it simple. Again, there are some things that I'm going over quite fast. Okay, I I don't want to make this class super long. So I'm going to be moving through some things a bit fast. But don't worry, because in case that you want to review everything with more detail, read all the different things that we are explaining here, all of you are going to have this project, so you can advance through the notebook at your own pace. Okay. In my case, I'm going to go a bit fast, just because I don't want to make this video, this online course, super long. Okay. All right. So I think that at this point you are ready to create your ROS2 program. Okay. Then let's go for it. Okay, so we already have our ROS2 package, yeah? Then the next thing that we have to do is to add a ROS2 program to our package. And here we have the first version of the code, very simple code, yeah? Then we are going to create this Python script, simple.py, inside our ROS2 program, okay? Then, remember, when you want to create a new ROS2 program, you should create it inside the package with the same name of, inside the folder, sorry, with the same name of the ROS2 package. In this case, it would be this folder, which already contains this init.py, yeah? So here in this folder, I'm going to right-click and select the new file option, and I will create here a new Python file named simple.py. There we go. Okay, so this creates this new empty Python file. And now what I can do is to just copy the contents here from the notebook and paste them here into, there we go, into my file, okay? All right. Here again, I'm not going to enter into how this Python code works. I'm going to assume that you already have a basic knowledge on Python programming, okay? So I'm not going to be explaining the details of all these different Python code lines, okay? In case you don't, I have left here a link for our free Python 3 for Robotics course that you can take completely for free in our platform, and this is going to give you all the base knowledge that you need to start programming with Python 3 for Robotics, okay? All right, so we have our ROS2 program. I'm going to explain very quickly what this does, but it's very simple. I will do it later. Then, once I have my package, I have my ROS2 program here, the next step is to create my launch file, right? So, for this, first of all, let me create a new launch folder, launch directory inside my package, yeah? You can do it directly here from the code editor or do it from the terminal as indicated here, it doesn't matter, whatever way you prefer, okay? So here I'm going to go inside my package and here I'm going to create a new folder, a new directory named launch, yeah? This is going to create the new folder here. And then inside the launch folder, I'm going to create a new file here named my package launchfile.launch.py. Okay? Let's create it. And there we have it. Okay? Always that you create a ROS2 launch file, it should have this extension, yes? .launch.py. To indicate that this is a ROS2 launch file and that it is written in Python format, okay? Because you can write ROS2 launch files in other formats such as XML, YAML, etc. Yeah, but this indicates that this is a launch file in Python format, okay? And then, final step here, you have a quick exercise. You can take your time if you want to do it. In my case, I'm going to go straight with the solution, okay, so that we can move faster. And this is how the launch file should look, okay? So let me copy the contents and paste them here to my launch file, yeah? So what do we have here? We have a launch file where we are launching an executable named simple, yeah? This executable contains our ROS2 program from simple.py, which is inside the my package, yeah, the package that we have created, and the output, I'm redirecting it to the screen. Okay? So I have my launch file, I have my program, I have my package, everything is ready. There is only one last step that we need to complete, yeah? Because here we are launching an executable named simple, yeah? But this executable doesn't exist yet in my package. In order to create this executable, I need to first compile my package, yeah? I need to specify some instructions to generate an executable from my simple.py program, and the executable has to be named simple, yeah, because this is the name that I am using here in my launch file, right? Then where do I specify these instructions? Well, you do it, as I said some minutes ago, in the setup.py file of your package, yeah? Here is where you are going to specify how some instructions to take into account when building this specific package, yeah? So let me go back here to the notebook, and here we have the final resulting setup.py file, yeah? Then basically here I am adding some things, a couple of things, let's say, okay? So the first thing that we are adding is this line here, okay? You can copy and paste directly the whole file. I'm going to do it line by line to show exactly what are the differences from the one which is automatically generated and what we are adding to this file. So, sorry, let me get this line, which is first addition. Then we are adding this here inside the data files, yeah? Let me add it here. What is this line doing? Well, basically this line is saying that I want to install in my package all the launch files with this extension, .launch.py. I want to install them inside my package, okay? Very quickly, because I don't want to go too much into advanced details, but whenever you build a package, this package is going to be generated inside the install folder of your workspace. Here, you can see it, yeah? So basically here, what I am saying is that I want to install inside here, yeah, all the launch files that are inside the launch folder and that have this extension, .launch.py. In this case, it's this file here, yeah? We are going to be installing it here. Why? Because later, when we execute launch files, the ROS2 system is going to look for them here in the install folder, okay? Step number one. Step number two is to generate the executable. We do this here with this line, yeah? Let me copy it and paste it. So here inside the console scripts, yeah, I'm going to add this line. What am I doing here? Okay, so here what I'm doing is, hey, I want to create an executable named simple node, right? From what? Yeah, from the main function, yeah, let me go to the simple .py script, from the main function, which is this one here, yeah, of the simple.py script, yeah, so from this, the main function of this Python script, which is inside the my package, yeah. So this goes my package, which is the ROS2 package that we have here. From this package, it's the simple.py script, this one here, and from this script, the main function which we have here, yeah? Then, from this, I am generating an executable named simple node, yeah? So whenever I execute this executable, what's going to be really executed is the contents of the main function, yeah, from my simple script, which is this one here, okay? All right, and then finally I need to add a couple of things. You can see it here in these warnings, yeah? So here I am using some classes that I need to import them, yeah? Here you can see the imports of OS and glob. So I need to add these imports also to my launch file. And that's it, okay? Now, with the modifications being made to this setup.py, we are ready to compile, okay? Then let me come here. Remember, where do you need to compile your package? It is in the root of the workspace, yeah? So here, in ROS2 workspace, not inside SRC folder, not inside the build folder, no, here, in the root, yeah? Then here I can execute callcon build, packages, select, and then my package, all right? Okay, and then always after building a package or building a workspace, you should source that workspace, okay? That thing that we were doing at the beginning before running programs, yeah, we were executing these source commands, yeah? So these commands basically what do is to activate, yeah, the unspecific ROS2 workspace, yeah? So here we have built this package from the ROS2 workspace. Now, in order to activate it, so make sure that ROS2 can access the latest version of this package, what we need to do is to run the source command for this workspace, yeah? You are going to have it probably here in the instructions, there you have it, yeah? The source command. So, source install setup.bash, yeah? The file that you are going to always source is the setup.bash inside the install folder. Okay, and finally, we are ready here to execute our program. So let me copy the command here from the notebook and paste it and run it. And this fails as it is expected. Okay, here, what is the error message? We can see it here. Code exception in launch. It says executable simple not found on the libexec directory. Yeah? So basically it says, hey, you are trying to launch an executable named simple, but I cannot find it. Yeah? And that makes sense, right? Because in my launch file, I am trying to start an executable named simple. But in my setup.file, I am creating an executable named simple node. Yeah? So this is not compatible, right? Then either I need to change here the launch file for simple node, or I need to regenerate here an executable named simple. Either of the two, okay? For example, let me just keep the name of the executable to simple_node, and then I need to update the name of the executable that I want to start here to simple node, right? Yeah? Then I have done some changes here in my launch file, then I need to recompile my package, yeah, for the changes to take effect. And of course, I need to source again. Okay, there we go. Now, let me try to launch again my program with ROS2 launch, name of the package, name of the launch file. Okay, there we go. And now this works, and all it does is to print here this sentence. Help me, Obi-Wan Kenobi. You are my only hope. Okay? Now, yeah, so this is basically what this program does. Okay? This is a super basic program. We have a main function. We initialize here the ROS2 Python client library. Then we have a print, a regular Python 3 print with a string here. And then we shut down the ROS communication. Okay? So, very, very simple program, just to get started of the process of creating a package, creating a new program, building it, executing it, etc. All right? Okay, then let's keep moving. Yeah, so here you have some more details about how to modify the setup.py file, okay? I have already explained this. But basically, the most important parts here are the entry points, yeah, where you specify the name of the executable, and then the name of the package, the name of the script, and the main function, yeah, which is going to be executed for this executable file, okay? And then also for the data file section, here you can install the launch files that you create for your package, okay? All right, now let's introduce a very, very, very important concept in ROS2, which are nodes, ROS2 nodes, okay? So what are ROS2 nodes? Well, basically, you can think of ROS2 nodes as ROS2 programs, okay? So every time you create a new ROS2 program, a new node is going to be generated, okay? And then the most important part here is that nodes can communicate with each other, exchange information using several methods. Yeah? One of them, which we are going to review in part 2 of this course, is topics, which is probably the most important one. Yeah? But basically, every ROS2 program is going to be contained inside a node. Yeah? And in any robotic system, you are going to have many nodes which are communicating between other, which basically means exchanging information between nodes, as you can see here. Okay. Now, the main command for checking what are the nodes available in a ROS2 system is ROS2 node list. Okay. So, for example, let's, in our case, execute this command here, ROS2 node list, and then this is going to list all the nodes that are ROS2 nodes that are currently running. Okay, you can see here Jazzy ROS control, controller manager, joint state publisher, etc. Yeah. Now, all these ROS2 nodes, who is providing them? Well, in this case, all these ROS2 nodes are being provided by our simulation. Yeah. The simulation that we have here running, by the way, my robot went somewhere. Probably it was moving on its own. Okay, never. There it is. There we have it. Yeah. So all these ROS2 nodes that we can see here with ROS2 node list are being provided by this simulation that we started at the beginning. Okay. Then our program is actually not starting any ROS2 node, right? So if you come back here, we can see that our program is not actually initializing any ROS2 node. Why? Well, because this program is not doing anything. Well, it's doing something, it's printing a message, but as soon as it prints this message, which takes milliseconds, it shuts down, yeah? So therefore, there is no ROS2 node left there, so that we can see with the ROS2 node list command. Yeah. So the very next thing that we are going to do is to update our program and give it a structure which looks more like a typical ROS2 program. Okay. Now here we have the code. Let me copy it directly from the notebook and paste it here into the simple pie. There we go. So this starts to look more like how a ROS2 program looks like. Yeah. Here we have the explanations on the code, so let me go over it. Okay, then let me review real quick here. All right, so now we have a class, a Python class named myNode, which inherits from the ROS2 node class. Yeah, this is a ROS2 class, which you can see we are importing here from the RCLPy, the ROS2 client Python library, yeah, which contains functionalities related to ROS2 nodes. Yeah, so we create our class which inherits from this one, and then here we are initializing a new ROS2 node named obi_1. Yeah, here is where we initialize our new ROS2 node with this name, obi1. Okay. Now here we are creating a timer. What is a timer? A timer is a function that is executed periodically. Okay. In this case, we are setting a period of 0.2 seconds. And of course, we have to associate to this timer a specific function. Yeah? These functions, which are executed periodically, are known in ROS2 as callbacks. Okay? So we create this timer with this timer callback function that we define down here, that is going to be executed every 0.2 seconds. Okay? And what are we doing here? Well, inside this timer callback function, what we do is to print the same message, but this time using a ROS2 logger, yeah, which is the proper way in ROS2 of printing log messages to the screen, to the terminal, okay? And finally, we have our main function, again, where we initialize the ROS communication. We create an object of our myNode class, yeah? Then we spin the node, okay? Which basically means that we pause the program execution, we leave it there running until somebody explicitly stops this program, this node, for example, by pressing Ctrl+C in the terminal, yeah? When that happens, what we do is we shut down the ROS2 communication, yeah? So basically, this is going to create an object of the class. It's going to start spinning this node, this one here, the OB1 node, and then what's going to happen is that our timer is going to start executing periodically this timer callback function, which is going to keep printing this message every 0.2 seconds. Okay? All right, so what do we need to do now? Well, we need to, first of all, recompile our package, right? Let's recompile it because we have done modifications to the code. We need to source our workspace to get the latest version of our ROS2 program, and then we can already start it. Yeah, there we go. And here we can see our program is printing constantly, periodically, this message, yeah, using this timer every 0.2 seconds. Yeah. So what's going to happen now if I open another terminal here? We leave our program running, we open another terminal here, and in this new terminal, we execute the ROS2 node list program. What's going to happen? Let's see. Okay. Let's see if my terminal loads. There we go. ROS2 node list. Okay, what do we have here now? Okay, so here we can see our node, yeah, OB1, which is running here, okay? What else can we do with our nodes? We can get information from the node. So with the ROS2 node info command, yeah? In this case, it's going to be ROS2 node info and the name of the node we want to get info from, which in our case is OB1, right? So let me paste this command here, ROS2 node info OB1, and here I get some information from our node. So does this node have subscribers? Does this node have publishers, services, actions? Yeah. So in a moment, in part 2 of this course, we are going to get into publishers and subscribers, okay? But basically, what we are doing here is to get information of our node, all right? Okay. So we have basically finished the part 1 of this course. Then let's close it by trying to answer this question. Okay, so what is ROS2? Well, basically ROS2 is all this environment infrastructure that allows us to exchange information from between nodes. Yeah, it manages all this ecosystem that you can see here of several nodes changing information between them. Yeah, and with this structure, which is really important, you can manage a whole robotic system. Yeah, because you are going to have several nodes. For example, imagine one node is in charge of getting the data from a robot's laser, yeah, and then this information from the laser of the robot can be sent to another node which is in charge of navigating the robot, right, and sending velocities to the wheels. This way, we can use the information from the laser in order to take decisions when moving the robot, for example, to avoid obstacles that are being detected by the laser. Yeah, and this is basically what ROS is about. Yeah, ROS 2 is about exchanging information between systems, between different ROS2 nodes to make a robot do something useful for us. Yeah? And this structure can go from a very simple robot or a very simple task to very, very complex tasks. All right? Okay, excellent. Then we are done with part 1. So let's move to part 2. So let me close my ROS2 node here. By the way, now if I try to check again this, of course, it's not able to find the OB1 node, right? Why? Well, because I have stopped it, okay? All right, so let me close part 1, and I'm going to go straight to part 2, ROS2 topics and multi-threading. Okay, so now that we have introduced some basic concepts such as packages, ROS2 programs, we have created our first basic ROS2 program, ROS2 nodes, we are going to see the main method that ROS2 uses to send information from one node to another, and this is topics. Okay, this is the main communication method that ROS2 relays on. All right, so again, for this second part, we are going to continue using the same simulation, okay? So we can leave it here running. Actually, I'm going to later restart it, okay? Just in case my robot is moving around. No, now it's stable, but I'm going to restart it later. But let's first see some basic topic commands, yeah? So we saw in the previous unit the ROS2 node list, ROS2 node info commands. So what about topics? Topics also provide a set of command line tools that allow us to quickly, from the terminal, interact with them. Yeah? For example, you can run ROS2 topic H to see all the different options that we have with the ROS2 topic command. Yeah? You can see them here. Then the first one is, of course, ROS2 topic list. In the same way as we have ROS2 node list, we also have ROS2 topic list. And what is this command doing? You can see it here. Output a list of available topics. So let's try this here, ROS2 topic list. And then here we have a list of all the topics that currently are running in this ROS2 system. And who is providing all these topics? Well, of course, it's again our simulation. Yeah? Our simulation that we have here running is the one which is providing all these topics. Yeah? Which provide information from many systems, from the simulator itself or from systems from the robot. Okay? For example, we have here the scan topic, which provides information of the laser that this robot has here mounted on top. Yeah? We have here this topic, ROSBot Excel base controller / command bell, which allows us to send velocity commands to the wheels of the robot. This is the topic that we used earlier to move the robot with the keyboard, okay? By sending information to this topic, okay? Now, let's start to see some more detailed things here about topics and about some specific topics. For example, this command bell topic that I have just mentioned, yeah? So if we want to get specific information about this topic, we can use, again, the ROS2 topic info command, and of course, provide the name of the command, of the topic. So ROS2 topic info, and then we provide the full name of the topic that we want to get more information about. Yeah? So here we can see some information about this topic. This topic uses this specific type of message. Yeah? So every topic is used to exchange information between nodes. Yeah? And this information is sent in the form, in the structure of messages. Yeah? There are many different messages, and topics can use the same message or can use different messages depending on the information they are transmitting. All right? For example, we can see that this specific topic has a publisher count of 0. What does this mean? This means that this topic doesn't have any publisher. Okay? What is a publisher? A publisher is a ROS2 node that publishes information to a topic, that sends information to a topic. Okay? We are going to get into much more detail, and we are going to create our own publisher and so on in a moment. Okay? And also we can see that this topic has one subscriber, right? Subscription count is 1. What is a subscriber? Well, a subscriber is nothing else than a ROS2 node that reads information from a topic. Yeah. So you can think of a topic as a channel, a pipe, through which information flows. Yeah. This information is sent in the form of messages with different structures depending on which kind of information. Yeah. It's not the same to send information about a laser than sending information about a camera, than sending information about wheel velocities. Yeah. Each type of information that we want to send through a topic is going to have different structures, so it's going to use different message types. Yeah, and then we have this topic which is used to send information through. Yeah, so these messages, this data flows through these topics, and then we have programs that can either publish information into these topics or read information from these topics, which are known as publishers and subscribers. Okay? So this is quite theoretical so far, but we are going to get into much more detail in a moment. Okay? For example, to demonstrate what I was saying, we can try to get information about another topic, scan topic, which is used to transport laser data. Yeah? You can see that the scan topic uses a different type of message. Yeah? Laser scan, twist stamped. Okay? And if I choose another topic, which is actually the camera topic, I think that we don't have it active, right? But for example, if we get information from the IMU, ROS2 topic IMU, you are going to see that. I forgot the info. ROS2 topic info. This uses another type of message. Okay. All right. Then we can directly subscribe to a topic from the command line tool, but by using this command, ROS2 topic echo, and then specifying the name of the topic. Okay? So let me copy this command, and I'm going to subscribe to this command bell topic. Okay? ROS2 topic echo. Yeah? Remember that this topic is the one used to send velocities to the robot. Yeah? So that it moves. Then, if I execute this command, I'm going to subscribe to this topic, which means that I'm going to start reading the information that is flowing through this topic. So let me do this. And nothing happens, okay? So I cannot see any information. So am I doing something wrong? No, this is normal. Why? Why do you think? Well, because right now, nobody is publishing information into this topic, right? Remember, when I checked the information from this topic, it had no publisher, yeah? So this means that there is nobody, there is no ROS2 program, no ROS2 node, which is publishing information to this topic right now. That is why I cannot see any data flowing through this topic, right? So, what could we do here? Well, for example, what we could do is to start the ROS2 command to move the robot, if you remember about it. Let me grab it very quickly from the notebook. So, for example, if I start the program that we used earlier to move the robot, here, let me put it here in a third terminal, yeah? So if I start executing this program, what's going to happen here? Let me send velocities here to the robot. Let me move a bit up. There we go. Okay, so for example, let me start here rotating the robot to the, there you go, yeah? So here we can start seeing information being published to the topic, right? Let me stop. There we go, yeah? So right now, this program, what does is to publish information to this specific topic. Therefore, I can start seeing the messages that are being published to this topic, okay? Another thing that I can do, let me stop this, is to manually publish messages to that topic, also through the command line, which is what we are reviewing here, okay? Now, before being able to publish a specific message to a topic, what do we need to know? Well, of course, what we need to know is which kind of information that topic uses, right? So, let me, sorry, it's ROS2 base controller command bell, yeah? So before being able to publish information into a specific topic, we need to know which type of information that topic uses, right? For example, for this specific topic, it is geometry messages, message twister stamped. Okay, this is the name of the message that it uses, of the interface, and this is the package which contains the definition of this message. Yeah. Now, we can, of course, know more details about how is the structure of this message with the ROS2 interface command. Yeah. ROS2 interface command line tools allow us to interact in the same way as ROS2 node and ROS2 topic, but in this case with interfaces, which are basically ROS2 messages. Yeah. So for example, we can run a ROS2 interface list, which is going to list all the available types of interfaces, messages that are available by default in ROS2. Okay. So you can see there are many of them. Or for example, here we can see the twister stamped. Yeah. And if we want to get specific information about one message, we can do the ROS2 interface show command and specify the name of a specific interface. In this case, for example, we are going to get more information about this twist stamped. Yeah, so here we can see the tiled structure of how this message looks like. Yeah, so we can see it has a header with some timestamps. It has a twist message inside, yeah, with some vectors defining linear and angular velocities. Yeah. So here I can know exactly how is the structure of these messages. Yeah. With this information, I can already create myself one message and publish it to this topic, right? And furthermore, I can use another command, which is ROS2 interface proto, to show me the exact formatting of the message I need to publish to this topic. Yeah, this is done like this. Yeah, so ROS2 interface. Let me paste it here. ROS2 interface proto, which stands for prototype of this type of message. Yeah, so basically this is going to show me a prototype message to be published into this topic. Yeah, as you can see, this is the same as we saw here published in our topic, right? So let me actually stop this because now I'm going to have nothing again in my topic, right? Because I stopped the program, now there is no messages being published here, right? Okay, so with this prototype, I am ready to construct a full message to publish into the ROSbot Excel base controller command bell topic. Yeah, here I have an example, so let me copy directly from here and paste. Yeah, so what am I doing here? Okay, ROS2 topic pop. Okay, this message can be used to publish directly a message into a topic from the command line tool. Yeah, so it's a counterpart of the ROS2 topic echo. ROS2 topic echo is used to subscribe, to read the information that is published into a topic, and ROS2 topic pop is used to publish a message into a specific topic. In this case, we are publishing into this topic, and what we are publishing, this type of messages, twister stamped, and then finally I have to specify the structure and the contents of the message. Yeah. So in this case, you can see here that I am publishing some angular velocities. Yeah, these velocities are going to make my robot rotate. Let me try to find my robot, where it is now. Where do we have it? Where it is? Should be somewhere around there, right? Okay, I completely lost it. There we have it. Okay, there we have our robot. All right, so let me come back here again. And then, once I start publishing these messages into the topic, what should happen? Well, what should happen is that my robot should start rotating. Okay, so basically, velocities for this robot, let's say that now it's working in a differential drive mode. So basically, I can send two types of velocities. Yeah, one is linear in the x-axis, which is going to make the robot move forward or backward. And the second type of velocity that I can send is angular in the z-axis, which is going to make the robot rotate to the right or the left. Okay? Then let me start publishing these messages here, and then two things are going to happen. First of all, I'm going to start seeing messages published here to this topic from my subscriber that I have created here in the command line. And second, I'm going to see the robot start moving, rotating, right? So let's go for it. Okay. There we see our robot starts rotating. And also, if I go to the terminal, I can see the messages being published to the topic. All right. Awesome. Okay. Okay, great. Then let me stop this. And let's continue. Okay. So here we are checking structures for other messages, like the laser scan. I'm going to move forward. Okay. Okay. So with all these tests that we have been doing, how can we define a topic? Well, the way in which I would define a topic, which I think it's easy to understand, it's that it's a channel where information flows. Yeah? And then you can either publish information to that channel, to that pipe, or you can get information from that channel, that pipe. Yeah? The ROS2 program or node that publishes information to that pipe, to that channel, to that topic is known as publisher, and the ROS2 node that gets information from that channel, from that topic, is known as a subscriber. Okay? All right, then here in our latest tests, we have been subscribing and publishing to a topic from the command line tools, okay? It is possible through commands to create a publisher or a subscriber, yeah, and publish information or read information from a topic. This is very useful for debugging purposes, okay, or for quick tests, but usually for more complex programs, what you are going to want to do is to create your publisher or your subscriber in a Python script or in a C++ script, right? In a program, let's say, in a proper ROS2 program. So this is what we are going to do right now. We are going to start by the publisher, okay? We are going to create a publisher inside the ROS2 Python program, yeah? All right, then let me stop the simulation, by the way, because I will restart it in a moment to test this. Then, okay, so for this, we are going to create a new package named publisher package, okay? So let me copy the command here from the example. Remember, always that you create a new ROS2 package, you should do it inside the source folder of the ROS2 workspace. There we go, ROS2 package create, amend Python, it's a Python package. This is the name of the new package that I will create, publisher underscore package, and then I am specifying some dependencies, such as RCLPy, standard messages, and geometry messages. Okay, these are the messages that I will be using inside my program. So let me create the package. There we go. Of course, it's going to appear here in my code editor as well. There we have it. And then next thing is to create a new program. We are going to name it, in this case, simple_publisher.py. So let me copy the name exactly here, and then create the new Python script here. Okay, I'm going faster because all these steps are the same as we did earlier. Yeah, we have our Python script. Then I'm going to copy the contents here from the notebook and paste them into my script. Excellent. Okay. Then I'm going to finish here the whole structure. So create the launch file. Let me create first of all the launch directory inside my package, and then the launch file here inside the launch folder. There we go. Okay. So now I have my publisher package with the launch folder, the launch file inside, and I need to fill in the contents of my launch file. Let me again copy them from the notebook directly. There we go. And obviously I need to update the setup.py. Okay, all these steps are exactly the same as we did earlier. Okay, so I'm going faster here. Yeah. So just a quick recap. We are creating this simple_publisher executable from our simple publisher Python script. Then we are installing the launch files again. In our launch file, we are launching this simple publisher executable from the publisher package. Yeah, the one that we have just created. And finally, we have our simple publisher.py. Yeah, this is the main program. So now let's review what are the contents of this program. Okay, let me close some things here. This, simple. Okay, there we go. So what do we have here? Okay, again, we have a class which inherits from the node parent ROS2 class. Yeah. Then we have the constructor of our class, where we are initializing a new ROS2 node named simple publisher. We have a timer, as we had also earlier. Yeah, here we are creating a new timer with a period of 0.5 and an associated timer callback function. Yeah, the new thing that we are adding here is this line here. This line is creating a new ROS2 publisher. Yeah, using the create publisher method. Then whenever you create a publisher method, you need to specify the type of message that you are going to be publishing, and of course the name of the topic that you are going to be publishing to. So you can see here that we are going to be publishing to this command bell topic messages of the twist stamped type. Yeah. And then finally we have here a QoS setting, which I'm not going to cover for now. Okay. Then we, of course, have to define the contents of our timer callback function. Yeah. So what are we doing here inside our callback function? Well, we are creating a twist stamped message here. Yeah. And then we fill the information of two specific fields. Yeah. First of all is linear x, which we are setting to 0, and angular z, which we are setting to 0.5. Yeah. So basically, this is very similar as what we were doing here in this command, if you remember. Yeah. So we are specifying that we want to publish into this topic this type of message, and then this is the structure of the message that we want to publish. Yeah. It's a twist stamped with linear velocity in the x-axis to 0 and angular velocity in the z-axis to 0.5. Yeah. But here we are writing all this in a program. Yeah. Then once we have defined the structure and the contents of our twist stamped message, we can call the publish method from our publisher object that we created here. Yeah. We call the publish method to publish the message that we have just defined. Yeah. So this message that we have defined right here, we are going to be publishing it to the topic. Yeah. This is the key line where we publish this specific message to the topic. Yeah? And this is going to be repeated every 0.5 seconds because this is a callback function which is attached to my timer. Yeah? And then finally, what I am doing here is also publishing a log message, yeah, indicating that I am publishing a new message. Yeah, this is just logging information. And then finally, we have our main function again, where we initialize the ROS communication, we initialize our class, we spin the node, nothing new, and then here, once somebody kills the program, we are specifically destroying this node. Yeah, and we shoot down the ROS communication. All right? Okay, then what do we need to do? Well, so basically, checking this program, what would we expect this program to do? Well, basically the same as we saw earlier here, right? So we should see the robot start rotating over its z-axis, yeah? So let me restart the simulation one more time because I stopped it, right? Let me restart it. All right. Excellent. Let me get a bit closer to the robot here. Too much zoom. Not too much far away. Okay, just a bit. Okay, enough to see it. Okay, so what do I need to do now? Well, I need to compile my package, right? So let's go to the ROS2 workspace and colcon build. Let me specify the package I want to compile, which is, what was the name again? Let me check. Publisher underscore package. Okay, so publisher underscore package. All right, so we build our program, and then we source, and we try to execute our program. Let me get the command from here for being faster. Okay. And we are getting an error. Okay, what's going on here? Do not panic because this is expected, okay? I want to use this to show you something. All right, so here we have an error message, which basically says something here about this message linear, right? It says attribute error. Twister stamped object has no attribute linear, yeah? And then it's showing me this structure here, yeah? So what am I doing here? Here I am creating a twister stamped object within this message MSG variable, yeah? Then from this variable, I am trying to access the linear field, yeah? What is the problem here? Well, the problem basically is the following. If we check again the structure, which I think it was the command here, yeah, we can check it here or also here, yeah? So if I check the structure of the message here, I can see that yes, indeed, there is a linear field in my message, and inside this linear, I have also an X field, yeah? But my message variable references the whole twister stamped message, all this, okay? Or all this. If I do the proto, it's the same. Let me do the proto command, yeah? Or all this, yeah? Then can I access directly the linear field? No, that is not possible. If I want to access the linear field of the message, I need to access first twist, yeah? So how this would go would be like this: message.twist, and then I can access linear, yeah? So there are here hierarchies within the twister stamped message, yes? In the first hierarchy level, we have the header and the twist message, yeah? Then once I access the twist message, I can access the second level, which is this one. Sorry. It's linear and Angular, yeah? And then from within linear, I can access the third level, which is X, Y, and Z, yeah? So if I want to change the value of X, I need to go twist, then linear, then X. And the same for twist, then Angular, then Z, yes? So first is twist, second is Angular, third is Z, yeah? I cannot jump from the higher level to X, okay? I need to go through all the variables, all right? Okay, now with this modification being made, let's rebuild our package. There we go. Let's source, and let me put again here my robot, and let me put it like this so that I can run my program, and I should start seeing the robot rotating, right? As we saw earlier. And there we go. So we start publishing the messages, and I can see my robot starts rotating, right? Okay. Excellent, excellent. Then we have seen here how to create a publisher from code. Of course, if you subscribe to the topic, you are going to see all the messages being published, but we already saw that earlier, okay? Okay, so what about the subscriber? Let's do the same for the subscriber. So let me create a new package where I'm going to host the subscriber code. Let me go here. Again, whenever I want to create a new package, very important, you need to go to the source folder, okay? So here I'm going to create my new package, subscriber package. I'm going to create a new Python script inside my package. So let me copy the name exactly here. In my code editor, subscriber package, I go to the folder with the same name and create the new file, simplesubscriber.py. Next step, I copy and paste the codes that are shown here in the notebook. There we go. I'm going to continue by creating the launch folder and launch file. Let me go like this. Okay. I have already done this several times, so I'm skipping and completing all this quickly. Then let me add the contents of the launch file. And finally, update as well the setup.py. Okay, so let's open the setup.py, remove and paste. Okay, so very quick review of everything. We are creating this simple subscriber executable file. We are installing the launch files. Here we have the launch file, where we are referencing the simple subscriber executable from the subscriber package that we have just created. And finally, we have the simple subscriber code itself, okay? So, what do we have here? Yeah. Again, we are creating our Python class, which inherits from Node. We are initializing a ROS2 node named simple subscriber, and here we are defining the subscriber directly, okay? By using the create subscription method. Now, when defining a subscriber, we need to basically specify three main things. Yeah. First, of course, is the type of message that the topic uses. Yeah. So what information I'm going to be subscribing to. Second is the name of the topic that you want to subscribe to. And third is the associated callback function. Yeah. So every subscriber has, by definition, a callback function associated to it. Okay. What does this mean? Because I am subscribing to this topic, yeah, every time a new message arrives to this topic, a new message is published to this topic, my callback function is going to be triggered, activated. Yeah. Here we have a last field, which is related to QoS, but I'm not going to go over this for now. Okay. And then, of course, we need to define our callback function. Yeah. So here inside our callback function, all we have is a logger. Yeah. So we are going to print a log message with the contents of the message that is being published to this topic. Yeah. So every time this topic receives a new message. Some ROS node publishes a new message into this topic. This callback function is going to be associated, is going to be triggered, executed, yeah. And as you can see, this callback function gets as a parameter the message that has been published to this topic, yeah. And here you can do whatever you want with this message. Of course, you can process it for I don't know, for object detection, whatever you want. In this case, we keep things simple. So what we are doing is just to print the contents of this message. Okay. And finally, again, we have the main function where we are initializing the ROS communication. We create an object of the simple subscriber class. We spin our node. And whenever somebody kills our ROS2 node, we are going to destroy it here, and we are going to shut down the ROS2 communication. Yeah? So pretty simple, okay? Then let's try this out, okay? So one more time, let's go to our ROS2 workspace. Let's build, let me try to get my colcom build command here, and now it's subscriber package, there we go. Source install setup bash, and then run the program here. Okay. There we go. Through the launch file. Okay, and there we go. We can see a bunch of numbers here, readings. Okay. What is this? Well, basically, this is the contents of a message published to the scan topic. Okay, so let me stop this. Now we can get more information very quickly here from the ROS2 interface show. It's the sensor messages and laser scan. Yeah. Here we are subscribing to the scan topic, which we set also at the beginning of the class, that this topic contains the readings from the robot's laser sensor. Yeah. Here on top of the robot, this is a LiDAR sensor. Yeah. Then this LiDAR has a ROS2 program which captures the readings from the laser and publishes them into this topic. Yeah. Into this scan topic. And then let me show it here, ROS2 topic info scan. Yeah. So you can see that the scan topic uses this laser scan message, and the laser scan message structure is something like this. As you can see, it's quite complex. It has many fields. You can see, for example, the angle, the minimum angle and maximum angle of the laser, the angle increment between laser beams, scan time, the minimum range and maximum ranges for the laser. Yeah, and the ranges, for example, this is probably the most important field, the ranges array of floats. Yeah? In this array, we contain all the readings of the laser for each individual beam. These are basically all these numbers that you can see here. Yeah? And how does a laser work? In case that you are not familiar with that, we have a brief explanation here that I skipped earlier, right here. Yeah? Here you can get a more detailed explanation. But basically, how a laser works is that it sends beams, laser beams, yeah? And then if these beams collide with an object, the beam is going to return to the laser, thus providing the value of the distance from the laser to the obstacle that is blocking the laser beam, yeah? And this is used very, very often in robotics for example, obstacle detection. Yeah, for mobile robots to be able to detect obstacles and being able to avoid them. Okay, so all these readings that you can see here are laser beams which are detecting obstacles. Yeah, at these specific distances. This is in meters. All right. Okay. Then we have seen how to create a publisher, how to create a subscriber from code with Python programs, how to work with different topics, common belt topic, laser topic. Now, here also, I have mentioned a couple of times about quality of service, okay? I don't want to enter into details within this course because I think that's a bit more advanced. But in case that you want to learn more about this QoS, which is a very important topic to have into account when working with ROS2, I have left also down here a link to our intermediate ROS2 course, which covers this much more in depth, okay? So in case that you are interested, you can check out our intermediate ROS2 course here in the construct, all right? Okay, now I want to do an extra exercise, which is combining a publisher in a subscriber into the same node. Okay, so far we have created one ROS node which contains a subscriber, another ROS node which contains a publisher, right? However, you can create a ROS2 node which contains a publisher and a subscriber, or even multiple publishers and multiple subscribers, okay? So you are not limited to one of each, yeah? And this is what we are going to do right now, to create a ROS2 node, a ROS2 program, which contains both a publisher and a subscriber, okay? And for that, we are going to try to create a program that avoids the obstacles to get out of the room without colliding, okay? So what are we going to need for this? We are going to use two topics. Laser, okay, the laser data to detect obstacles, and then we are going to process this data, and we are going to publish velocity informations to the robot so that it is able to avoid, change the direction and avoid these obstacles, yeah? This is the objective of this exercise, okay? So you can try to do it on your own, of course. If you have time, I really encourage you to do so, because that's how you are going to learn the most. For this example, I'm going to use directly the solution, okay, and show it to you. Okay, then let's create a new program here, a new package, sorry. Here I have the command directly. So let me go again to the SRC folder, important, and create a new ROS2 package, which, let me close all this to clean up a little bit everything. And here we have our third package, which is named Robot Patrol, okay? Then here I'm going to create a patrol.py script. There we go, inside the Robot Patrol folder, new file, patrol.py. Here I have the code, which I'm going to directly copy and paste here. And do I have the launch file and everything here? Yes, I have it. So let me create all these. Create the launch file. Fill the contents of the launch file. What am I doing here? Sorry. Launch file. There we go. Okay. Okay, yeah, and here we are introducing a new feature, okay? Not a new feature, a new attribute for our launch file. So far, we've been using package executable and output. Here we are adding this emulate TTY, and we are setting it to true. What does this special attribute do? Well, basically, this enables colored log messages, yeah? So whenever we print logging messages in ROS, they are going to show in different colors based on if they are regular debug messages, warning messages, error messages, yeah? So to provide a bit more of context. And this is going to be helpful also for later when we analyze multithreading, all right? Okay. Then again, there are many more things that you can use and add to launch files, like pass parameters, special parameters to launch files. If you are interested in that, again, I'll leave you here the intermediate ROS2 course to have a look to all those things much more in detail, okay? All right, then we have here the setup.py, so let me update again the setup.py. There we go. And then last thing missing is to compile. And actually, I'm going to already compile here. So there we go. source. Okay. And then before executing this, what I'm going to do actually is to review the code. Okay. So let me open here and let's try to see what this code has, which is a bit longer than usual, but not much. Okay. So, all right. One more time, we create our class which inherits from node. We initiate our ROS2 node named patrol_node in this case, right? Then we declare our subscriber, which is going to subscribe to the scan topic using laser scan messages and with the laser callback function associated to it. Second, we declare our publisher, which is going to publish twist stamped messages into the command bell topic. Okay, we have already seen this in the individual examples. And then we are creating here a timer, named control timer, which is going to execute every 0.5 seconds and with a callback function associated to it, named motion. Okay. Now down here within the constructor, still we are initializing a twist stamped message. Okay. With the velocities to 0. Note that we are doing it correctly here now. Yeah. So we access first twist, linear, and X. Yeah. Also here we are setting a couple of helper variables for the minimum distance and sight threshold. This is for analyzing the laser data, and also this is for analyzing the laser data, for storing the different beams. Okay? Then here we have the callback for the laser subscriber. Yeah? What are we doing in the laser subscriber callback? Well, basically what we are doing is to access different values in the ranges array. Yeah? So we review it that laser array messages, right? ROS2 interface show sensor messages message laser array. No, it's laser sensor, sorry. Laser scan, that's it. Okay, laser scan messages have these ranges array which contain the values of all the beams of the laser. Yeah. Then depending on which value of the array we get, okay, we are going to be accessing to a specific direction of the laser. Yeah. So depending on the value from the laser that I get, let me go back to the picture here. Yeah, depending on the value that I select from the array, I'm going to be getting the values from one specific orientation. Yeah, so from the left side or the right side or the front of the robot. Yeah, all this is controlled through these values. Yeah, then here, for example, the position 2246 from the ranges array corresponds to the right side of the robot. Yeah. Let me actually restart the simulation here to have the robot properly oriented. Yeah. Okay. There we go. All right. Okay, so if I access the this specific position in the ranges array, I know that I'm going to be monitoring the right side of the robot. Yeah, so this side of the robot. Okay. If I get the value in the 0 position of the array, I know that I am analyzing the front of the robot. Yeah, so the laser beams in this direction of the robot, and if I analyze this position, I'm going to be analyzing the left side of the robot. Okay, you can get these specific values and what side are they associated to with different methods, mathematical methods, analyzing the minimum, maximum angle and the angle increments. Okay, you can look for that. I'm not going to go into too much detail about that. Okay, and then here I am printing the front of only the front value of the laser. Okay, then we have the motion callback function, which is the one associated to our timer, if you remember, which is going to be executed every 0.5 seconds. Yeah. Then what are we doing here? Here, basically, we are analyzing the values of the left side, right side, front side. Yeah? And comparing them with the thresholds that we defined also here in the constructor. Yeah? Then, for example, if the left side is lower than a side threshold and the front is higher than the minimum distance, we are going to reduce the speed and turn the robot. Okay? Yeah? Then, for example, this one, which is very clear, this is basically the logic, okay? The motion, the control logic of our program, yeah? So based on these laser readings, I'm going to tell the robot to do this in order to avoid obstacles, yeah? For example, if the front value of the laser is higher than the minimum distance that I accept, then there is no problem, no risk, right? So, okay, everything is good, keep the robot moving forward, right? Otherwise, if the front value of the laser is lower than the minimum distance, for example, the minimum distance, we have it set to 0.55. This is meters, yeah? So if my front laser reading is detecting something closer than 0.55 meters, hey, wait a moment, danger, because we are going to collide with it, yeah? In that case, stop the robot and start rotating in order to avoid the obstacle, right? So this is basically what we are doing here, yeah? We are analyzing the values that we are getting from the laser, and we are using some thresholds to make the robot take a decision, yeah? So if I detect that my robot in the front direction is about to collide with something, yeah, then hey, I'm going to stop, yeah? So not 100% stop, as you can see here, but basically we are reducing a lot the speed by multiplying by 0.25, yeah? So I reduce a lot the speed and I start applying an angular velocity, yeah, to make the robot start rotating to avoid the obstacle, yeah? Okay, actually, in this case also we compare the sides, yeah? We compare the readings from the left side and right side to see which side should I better rotate, yeah? Obviously, the side which has a higher value is the one that I'm going to choose to rotate, yeah? And this is the helper function that I have created here, yeah? A very simple function where I compare left with right, yeah, to the side which is the side of the robot which is more clear of obstacles, yeah? Okay, then finally, again, we have the main function where we initialize the ROS communication, we create the object of our patrol class, we spin the node, and then here we have a try exception here to catch any kind of exceptions, for example, the keyboard interrupt, yeah? In which case we are going to destroy the node in case that somebody stops the program by pressing Ctrl+C, basically, and then we are going to shoot down the ROS2 communication, all right? Okay, so having analyzed this program, let's try to run it and see what happens. Yeah, so here we have our simulation. Let me get a bit outside here and have a top view of this. Maybe we can also make this a bit bigger. Okay, so this way I think that we're going to be able to more or less see what's going on here. All right. Okay, so let me here execute my program then, which I have it down here. It's this one here. All right. So let's execute the program. There we go. All right. So our robot starts moving forward. As you can see here, we can see the readings of the laser. Yeah. So we are moving forward at quite some speed, and then once the front laser starts detecting this coach closer than 0.55 centimeters, the robot should stop and start rotating. There we go. We can see how it stops. It starts rotating, and there it's having some problems. It's colliding a bit. I think it was going too fast, probably. We can see here some messages with different colors as well. Yeah, so here it's detecting the infinite value, so it's not going to do anything. Let's try a second attempt, okay? So this program, obviously, it's not perfect, okay? I mean, it has been created quite. It's pretty simple, okay? It could have much more safety methods, control methods, etc. But for the purpose of explaining this example, I think that it's enough to see how to combine a publisher and a subscriber, and see how to create some basic logic, okay? Then maybe what we can do is try to reduce a little bit the linear speed to, I don't know, maybe 0.35 to make the robot move a bit slower. For example, let me do this live, Qualcomm build. Okay. And wait, let's launch again the program here. Okay. Then let me get a top view here. There we go. All right, so we have our robot moving forward again. And yes, we are going to see for sure that when it detects the coach, it's going to stop and start rotating. Here we can see the front distance for now, it's 2.0, 19, 18, 17, how it's decreasing. And as soon as it gets below 0.55, which is right now, it's going to stop and start rotating. There we see it, okay? As you can see, it keeps moving a bit forward, so that is why it might cause some problems. But we have fixed basically this, yeah? So now by reducing the speed, we are able to successfully avoid the coach and get out of the office without any problem, okay? We are not colliding with the coach, and our robot is able to safely get out of the office. Okay, I'm going to stop it now just so that the robot doesn't go to the end of the world, okay? All right, so we have seen the example of how to combine both publisher and subscribers into a same ROS2 program, okay? Now, yes, so here also I have a reference to another course, because so far we have been working with laser scan, twisted stamp, and messages, which are predefined messages provided by ROS2, but you should know that you can also create your own custom message types, okay? But that's, we are not going to be covering in today's course. So, in case that you are interested in that, you can have a look also at our ROS2 Basics in 5 Days Python course, where we show you step by step how to create your own custom messages, okay? Now, we are at the end of this second part of the course, which is understanding multi-threading and callbacks in ROS2, okay? So this is a super, super important topic in ROS2. It's a little bit complex, but we are going to try to at least explain the basics in an easy to understand way, and especially in a practical way, okay? So for this, we are going to create a new example, okay? We are going to create a new program, which is multithreading.py, and we are going to paste the following code, okay? I'm going to use the same program that I have here, the robot patrol, the same package, sorry, new file, multithreading.py. And then here I'm going to copy and paste this code. All right. So, sequentially. Okay. Yeah, so basically, in this example, we are going to show a specific example case, okay? So, what are we doing here? What we're doing here is that we are going to add an additional callback function, okay? It's this here, yeah? So, this is the code, the new code, which is basically the same as before with this addition, okay? Let me go over the code. So here you can see that we are adding we have the laser subscriber, the command bell publisher, we have our control timer, and then I have added another timer, which I'm naming process video timer, okay? This is a timer that executes also every 0.5 seconds, and then it has a callback function associated named process video, yeah? Then what are we doing in this process video? We have it down here, everything else is the same, okay? Here we have the process video callback where we are logging a message named processing video, and then I have added a sleep of 3 seconds, okay? So this callback that I have added here, this timer callback, I want to represent a callback which takes longer than usual to be completed, okay? Because this is going to present a problem, which we are going to see in a moment, okay? So far, we have been working with with very few callback functions and callback functions that are executed very fast. So we have not seen this problem. But what happens when we start introducing more callbacks to our ROS2 programs, and especially callbacks that take longer to complete? Yeah, for example, processing a video is a heavy task which might require more time than usual, than a few milliseconds to be completed, right? Then let's see what happens in these cases, okay? Let me complete this, this exercise by creating a launch file and editing the setup. So, okay, let me come here very quickly. I'm going to duplicate my launch file. So let me rename this as I'm going to name it as I was naming it multithreading.launch.py. Okay. Multithreading.launch.py. Okay, there we have it. And then this is Robot Patrol, the executable name. I need to add it, so let me add it here. Then I'm going to copy this, comma, and add a second executable. Okay, this is something that you can do also when you have several programs in the same package. Yeah. So this is going to be multi-threading node, right? Yeah. Multi-threading node. This is the name of the executable, and the name of the program is multi-threading instead of patrol. Okay, so I think I have it correct like this. I need to update the name of the executable here to multi-threading node. Right here. There we go. Okay, I think we are ready to execute it. Then restart the simulation. Recompile the package. There we go. And let's see what we have this time, right? So we have our simulation here. Let's source. And let's execute not this, but the multi-threading.launch.py. Okay. So what can we see now? Now we can see an interesting behavior of the robot, see? The robot is moving forward and stopping every few seconds, see? It moves and it stops. It moves and it stops. And if we see the callbacks execution, we can see that the program is executing, but once it reaches the processing video callback, it gets blocked. Yeah? It gets blocked for exactly 3 seconds. Yeah? Every time the program is executing this process video callback, it gets blocked for 3 seconds. What does it mean? This means that the other callbacks, like the motion, which contains the control, or the laser callback, are not being executed, okay? And this can be a huge problem, right? Why? Because my robot might not be able to react in real time, okay? Here, probably it's going to be able to solve it, or no, we'll see. Well, actually, it's starting to do something strange. It's crashing there against the coach, okay? Why? Because my processing video callback is blocking the other callbacks from executing. So the robot doesn't get the laser data in real time and is not able to react in real time to these obstacles. Yeah? And this, as you can see, can be a huge issue in robotics. Okay? Then how do we solve this problem? We solve it with multi-threading. Okay? Here you can see a graphical representation of what is happening. Yeah? So we have the three callbacks here of our program: laser callback, motion, and process video. Yeah? Then laser callback gets executed, motion callback gets executed, and then process video gets executed. The problem is for 3 seconds, my process video callback is blocking this one from being executed. Yeah? The motion callback should be executed every 0.5 seconds. And it's not being executed every 0.5 seconds because it's being blocked by this one. Yeah? And why does this happen? Well, this happens because by default, ROS2 uses one single thread. Okay? So all the callbacks are executed in the same thread by default. Therefore, if one specific callback is blocking the thread, the others cannot be executed. Right? So how do we solve this? Well, by using multi-threading, right? And then we can try to execute one callback in each thread so that we don't have this problem, right? That would be the logical solution. Then we are going to try this in the next example, yeah? Then basically in ROS2 we have two types of executors, okay? Single-threaded executor and multi-threaded executor. Yeah? Then by default, this is used in ROS2. If we don't specify anything, which is our case, here we are not specifying any specific executor or anything related to multi-threading. So by default, the single-threaded executor is used. Yeah? So what we are going to do is to use the multi-threaded executor for our example. Okay? Then let's update our program with a couple of things. First thing, you can copy and paste. Well, actually, I'm going to do it as well, just to go faster, yeah? So let me update this program and just show you what I am adding, okay? So what are we adding in this new version of the program? Well, first of all, we are importing the multi-threaded executor, okay? Here. And then we are defining it in the main function, okay? Here, as you can see, we are creating a multi-threaded executor object, yeah? And then what we do is that we add our patrol node to this multi-threaded executor, yeah? And then let me show the comparison with a regular program here, yeah? So in a regular program, we create our node here and then we spin our node directly, yeah? When working with executors, what we do is to define the executor, in this case as multi-threaded, then we add the node to the executor, and then we spin the executor, not the node. Yeah? We spin the executor. And then, of course, we also need to shoot down the executor. Okay? Yeah, so these are the only modifications from this program. Yeah, you have it here. Yeah, so we are importing the multi-threaded executor, and then we are creating our multi-threaded executor and adding the node to our executor. So far, this is the only modification that we have done. Okay, then let's see what happens. Let's try to recompile our program here. Let me, yes, I need to recompile the program like this. Source. Let me restart the simulation also to bring the robot back to the starting position. Here we are. Okay, there we go. Let me go again to a top view to see what's going on here. Zoom a little bit. Not so much. There we go. Okay. And then I can relaunch my program, this time using a multi-threaded executor. Right? Okay. So let's execute it and let's see what happens. Okay, so what happens? My robot continues moving in intervals. See? So it moves a little bit, it stops. It moves a little bit, it stops. And if you check the callbacks execution, it's happening exactly the same, right? So every time we have the processing video callback running, the others are blocked. Okay? Indeed, in this specific case, we can't even get the response from the laser, which is even worse, right? So the processing video is blocking the other callbacks. Yeah? So we have the same problem. Okay, but then what's happening here? Let me stop the program already. What's happening here? Alberto, you might be asking. Okay, this is because using multi-threading only it's not enough. Yeah? So we need a second concept, which is callback groups. Yeah? In order to enable multi-threading in ROS2, you need executors first and callback groups second. Okay? Why? Let's show an example to try to explain this as simple as possible. Yeah? So basically in ROS2 you have two types of callback groups, mutually exclusive and reentrant. Okay? What are the characteristics of these callback groups? Well, for the mutually exclusive, callbacks within this group are guaranteed to never run concurrently, in parallel. Yeah? This means that only one callback in the group can be executed at a time, even in a multi-threaded executor. Yeah? This is very important. Only one callback in the group can execute at a time, even in a multi-threaded executor. Yeah? Then this is useful when callbacks share resources or data structures that are not thread safe, ensuring no race conditions occur. Yeah? On the other hand, the reentrant callback group has the following properties. Yeah? Callbacks in this group can run concurrently even with other callbacks in the same group. This allows maximum parallelism provided the callbacks are designed to handle concurrent execution safely. Yeah? Reentrant groups are ideal for stateless or thread-safe callbacks that do not rely on shared mutable resources. Okay, then by assigning callbacks to these groups using a multi-threaded executor, developers can control the level of concurrency in their applications and ensure efficient and safe execution of tasks. Yeah. So basically, by enabling multi-threading, yeah, what I am doing here is giving to my program the possibility to use multiple threads. Okay. Now, by using callback groups, what I can do is control and manage how my callbacks are going to be executed. Okay? Then what happens here? Here, what happens is that by default, if we don't specify any callback group, yeah, by default, ROS2 uses the mutually exclusive callback group. Why? Because this is the recommended way of working, okay? You can use reentrant, but reentrant can't have some problems, especially for more complex ROS programs, okay? So if you use reentrant, you have to be 100% sure that your callbacks are thread safe, okay? And they do not depend of other callbacks. They don't need to wait for another callback to execute first and change some value, okay? Because basically in reentrant callback groups, everything can run simultaneously without any control, yeah? So basically it's like party, yeah? There is no control over callbacks. Everything can be run as the system wants, yeah? Then usually, when creating ROS2 programs, the recommended approach is to use mutually exclusives, okay? And this is the one that is used by default. So in my case, my callbacks are using a mutually exclusive callback group, yeah? What is the problem? The problem is that all the callbacks are in the same mutually exclusive callback group. Yeah, so scan, laser callback, motion, and process video. The three callbacks, all of them are in the same callback group. Yeah, all of my callbacks are in the same mutually exclusive callback groups. And as it is stated here, yeah, only one callback in the group can execute at a time. Yeah. So because all of the three are in the same mutually exclusive callback groups, only one can be executed at a time. Therefore, we still have the same problem. So how to solve this? Well, the solution is to create separate mutually exclusive callback groups. Yeah? And this is what we are doing in this final example, which is the correct way of solving this kind of situation. Yeah? So let me copy the program one last time here. Let me update the contents. Yeah? And then this is the same code as before with our multi-thread executor. We are at the node, etc. And the only difference here is up here. Yeah? So first of all, we are importing the mutually exclusive callback group. And then here what we are doing is creating two separate mutually exclusive callback groups. Yeah? We are creating one callback group for the motion callback and another callback group for the video group. Yeah? And the laser one, which we have here, is going to run in another one, in a third one, which is the default one. Yeah? So we have this laser callback executed in the default mutually exclusive callback group, and then I am creating two additional mutually exclusive callback groups, one for the motion callback and another one for the video group. Yeah? So when I define the motion timer, right here, I specify this timer to use this callback group, the motion group. Yeah? And when I create my process video timer, I specify this timer to use the video group. Yeah? So now I have each callback being executed in a different callback group. Yeah? This means that I no longer have this limitation, that only one callback in the group can execute at a time, because this only applies for callbacks in the same callback group. If I have different callback groups, even if they are mutually exclusive, they can run in parallel. Yeah? And this is the correct approach and the recommended approach for handling this kind of multi-threading situations and having callbacks blocking other callbacks. Yeah? As you can see, this is the only modification that we have done. Yeah? Creating separate mutually exclusive callback groups and applying them to the different timers. Okay? So, sorry. Let's one last time compile our package. I'm going to restart the simulation one more time, just to reset the robot's position, right? And then, there we are. I need to run this. Okay, so let me get a top view of the scene. Oop. Not so much zoom, a bit less. There we go. Okay, and let's execute again our updated program, which is now, remember, using multi-threaded executor, but also properly configuring the callback groups. Yeah. Then let's execute the program. Okay. And now we can see the robot is moving properly without stopping, yeah, without doing weird stops. And also we can see that all the callback functions are being executed properly without the processing video blocking the other callbacks. Yeah. So all the callbacks are being executed properly and concurrently. Okay? And I can see that my robot is properly detecting the obstacle. Well, here it had some problems. Never mind, yeah? You can see how the callbacks are being executed properly in parallel, and especially how the processing video is not blocking the execution of the other callbacks. Okay? Yeah? And how does this look like in a graph way? I like to, I added these graphs because I think they help clarify, yeah? So the scenario that we have now is the following, yeah? So we have the process video, still with the sleep, yes? We see it. Yeah, we have still the sleep here in our process video, yeah? So the process video callback is being executed for 3 seconds, as we can see here, but this is not blocking the other callbacks from getting executed every 0.5 seconds, in this case, in parallel, each one of them in different threads. Yeah? All right, so we have reached the end of the part 2, okay, which is basically my part. For the next part, you are going to be learning with Ricardo, my colleague. Now, just to close, let me tell you that this is so because of time limitations, obviously, we cannot go over many things, like, for example, services or actions. We have covered topics, but there are other methods of communication in ROS2, very important also, such as services and actions. In case that you want to keep learning other methods beside topics, I have linked here our ROS2 Basics in 5 days course, again, where you can keep learning about services, actions, or seeing more examples also of how to use and apply multi-threading to ROS2, for example, using reentrant callback groups, etc. Okay, so if you want to keep learning, please have a look at the courses that I have been linking here through the different notebooks. So yes, I'm going to, in my case, leave it here. I hope that you have enjoyed these basic concepts and introduction to topics and multi-threading. Again, I have gone a bit fast to try not to make this super long, but you have all the materials, all the notebooks, so please feel free to review them at your own pace, keep working on your exercises, changing the code, trying to improve it, etc. Yeah? By practicing is how you are going to learn the most, and this is why we provide to all of you this ROS project, so that you can have it, and you can directly start using it and working with these simulations, these programs from your computers without having to worry about installations and anything. Just get the share link and start learning, start practicing. All right, so yeah, I'm going to leave it here and pass it to Ricardo to continue with the next sections of the crash course, which are going to be part 3, 4, and 5.
Now, let's continue with the next lesson of this ROS2 Jazzy Crash Course 2025, Part 3, Visualizing Robot Data with RBase. So let's click on there, and then a new tab is going to open with this other notebook that contains the part about debugging ROS programs with RBase. RBase is the main tool that we are using when we try to find bugs into our ROS code. So it's inevitable that you will have problems and you will have to check your code. But then in robots, it's more difficult than in regular computers programs. So for that, we need a visualization tool that allows us to visualize what is happening with the robot. And that tool is RBase. You can see all the status of the robot, the sensors, the environment in that tool, so you can see if the robot is experiencing a strange situation and why is the reason. So let's start by launching the simulation. The first thing is to launch the simulation so we can continue in case that you haven't launched it before. So this is the command. I'm going to copy everything. Okay, so here. And then go to the previous tab where is the desktop and open a terminal on this icon at the bottom, and then launch. I'm going to paste the commands, and this is going to launch the simulation. I'm going to close this notebook, which is the main notebook that we provide, because we don't need it here. So let's see how the simulation opens. Should appear automatically. Yes, here it goes. And that's it. There it goes. So now it's loading the simulation, and then let me go back to the notebook. I'm going to be following the instructions here. So the first thing is that for example, if you try to do a ROS2 topic echo scan that you learned with Alberto on the previous lesson, then you should be able to see this kind of data, right? So this is in order to see the laser, the scan, the LiDAR information. It's a lot of data with numbers and intensities and so on, and that's okay. So we can use this information sometimes for some things, but actually we cannot see if the robot is actually detecting the proper things or not with the LiDAR. We cannot see if there is a problem in the LiDAR, for example. That is a better way of detecting when we can see the points related to the robot in a graphical way, right? So that's what RBase allows us to do. So let's do it. So let's launch this tool that is called RBase 2 because ROS2. Then we are going to launch the RBase. This tool is provided by ROS. When you install ROS, this tool comes along. And the command is very simple. It's RBase 2. That's it. So let me source also. I'm going to copy the source command because I don't want to type it. Oh, wait, by the way, we need to do this source specifically in this example because this source is allowing RBase to access the models of the robot. If you don't understand this, don't worry. This is just a crash course, okay? We cannot explain everything. Just copy this command and go into a terminal, a new terminal. I'm going to open in a new tab because we need to launch RBase in a different tab. Then I'm going to paste the command. This is just a source for this particular project. We need to have this source. Okay, in this simulation workspace, we have the simulation. And because for this particular project, we need to do this source. But usually you will not need to do that in your regular installation. Then we are launching the RBase 2 command. So you can copy or just type it. And then RBase is going to appear. Here we have the simulation that has appeared and the robot there. Now we are going to visualize the information from the robot itself. Great. So now we have the RBase that has appeared here. Let me put it by double clicking on the blue bar and putting to cover the whole screen. Okay, great. But now here we can see nothing yet. Why? Why is that? So I want to see my robot. I want to see the LiDARs. I want to see the camera, so on. Okay, so how do we do that? Then this is the screen that we get by default when you launch it. And then here we see several things, several information. The most important information is the one that is shown in this area. This is the one that allows us to configure the RBase, what is going to be visualized. And also this add button that you can see here, add button is the one that allows us to include in the list here of visualizers. The visualizers are specific modules that we are going to be adding there in order to see things. So when we want to see the LiDAR, we are going to add the visualizer for LiDARs. When we want to see the robot, we are going to add the visualizer for robot models, and etc. Okay, so you are going to see in a minute. Okay, then let me continue. Yes, the first thing that we are going to do before we start adding new visualizers is to change the fixed frame. Okay, fixed frame. What is the fixed frame? The fixed frame is this option that you can see here. The fixed frame, now it says map. This is the frame from which all the data is going to be displayed. So, for example, if I want to display the LiDAR ray number 30, then I need to say here from which frame, reference frame, right? Which 3-axis coordinates we need to display this data, because depending from which frame, the visualization will be one or another. It's not the same data of me watching, detecting the mouse than Alberto from another position detecting the mouse, right? The distance is different, the orientation is different. So that's the concept of frame. We are going to learn more about frames on the next section with me. I'm going to teach you about this. But now, here it says that the fixed frame is map. Then since we don't have the robot with a map, we haven't created any map, this frame is wrong. So if you click there and pull down the menu, you will see that there are a set of frames. Then now what we are going to do is to select the base link frame. The base link frame is the center of the robot frame. So whenever there is a robot, the center of the robot, that's called the base link frame. So we are going to be representing all the data from the center of the robot now. Okay, so far so good. Then let's continue. What else? Oh, yeah, now we are going to start adding visualizers. And the first one that we are going to start adding is the model, the robot model. So we can see our robot on RBase represented on RBase. For that, we go to the Add button, and then on the list of visualizers appears on the center on the screen. You select, go down until you see robot model. Robot model. Then press OK, and then nothing happened. Okay, yes. Why not? Yeah, because still we need to configure this visualizer. Then here you see that on the list of displays, okay, I'm going to call them displays because displays is better rather than visualizer. Then this display is, we can open down a drop-down menu, and we see there are several things for configuring it. We are not going to see all of them. You will see in the future by yourself. But the important thing is this one that says description source. It has to say topic. And then description topic, if we click on the side, we can have a drop-down menu and select the only option that we have is robot description. So if you press enter, it should appear there. And here we can see the robot model that is being displayed. Okay, yes, so far so good, right? Great, excellent. So now, what does it search for? So sometimes your model file of the robot is wrong. Maybe you have put the LiDAR in a different position. Maybe there is some problem with the wheels on the model. Then if your model visualizing is wrong, is not correct, it doesn't correspond to the proper robot, then you know that there is some problem. And this could lead to other problems later. Because if the LiDAR is not at the proper location, for example, then the computations for creating maps will not match. So that is why we need to visualize the model and to see it properly on the screen. If it is not showing properly, you need to check. That's the first way of debugging with RBase. Check that your model is properly working. Okay, so far so good. Let's continue with the next thing, with the next visualizer that we are going to add. So in these sequences, you can see that I have explaining about that. You can check the notebook for more details later. Now let's visualize the LiDAR information. So for that, we need to add another display here on Add. And then now on the list, we are not going to select this one on the list. We are going to change to the other list by topic. This list is more convenient right now because it provides us with the properly configured topic data. So let's go down until we see the scan. You see, this is the topic scan, and then select the one that is underneath, laser scan. Great. So now you see that some things appear. This is the LiDAR that is being computed by the robot in the simulation. And we can see how it shows the whole structure of the office. Of course, it is detecting itself here, some parts of itself, and that's why this is being displayed. Okay, but no problems. So this is correct. So that more or less shows the structure of the office that we have here, right? You can see here the corner, that is the round corner. Oh, sorry, I zoom it out. Now I did it too much because it's a little bit slow. So you have to take care about this. Okay. Great, so this round part is the one round part that we see here. The robot is facing in this direction. So everything looks quite correct, right? Great, then let's continue with the others. And that's the LiDAR, the scan, the laser scan that we have done it. And then there are some things that we haven't explained properly, which is the QoS settings that needs to be set to reliability policy, and the best effort also that needs to be set. And on the QoS, these are some configurations that you need to do inside the laser scan. That is why I decided to show you that you better select the display that is added by topic, because it's already automatically configured in this way. If you want to use this with your own robots, maybe you will need to check this. It's on the topic section within the laser scan. Then you have the reliability policy, which is reliable, and the durability policy, which is volatile. And that's what the notebook is mentioning here. And that depends on the LiDAR, the laser scan that you are using. So some LiDARs, they are configured in some way, some others are configured in other ways. So if you add this for your robot and you still don't see the LiDAR, check the values here correspond to the ones of the LiDAR. And how you can do that? Well, going to a terminal and then opening a new terminal and then doing an info of your topic. So if you do a ROS2 info of the scan topic, there it goes. So if we check now here on the scan, we can see, we need to check the one that is publishing, okay? So because there are several entries, it depends on some ones that are publishing and others are subscribing. But the one that we want to match is the one that is publishing. It's publishing the LiDAR data. And this is the one. It's the one provided by the simulation plugin for the LiDAR. And then it's a publisher here. And then we see that is reliability reliable and durability volatile. And those are the parameters that you have to match in the RBIS configuration, reliable and volatile. Okay, so, well, this is just giving you some data in case that you want to debug. You cannot see the LiDAR, then you have a problem there. And could be that it's just a configuration on the RBIS, or if you configure this properly with the proper reliability and durability and proper name of the topic, then you should see the LiDAR. If you don't see the LiDAR, then you have a problem there, and you can investigate more about what is happening. Maybe the LiDAR is not publishing or else. Okay, great. So now let's go and let's do something else. Let's visualize the frames of the robot. This is also very important in order to see if you have computed, if you have put it all the frames properly. So when you use TF, that we are going to see on the next lesson, what is this about? If you use computations based on the frames of the robot, they are correct. Because if the frames are not put into the proper place, then your calculations afterwards from that, they are going to be wrong. So how do we visualize the frames? By adding a new TF display. And for that, let's go. Let me minimize this, the laser scan, so it doesn't cover the whole screen, and also the robot model. And now I'm going to add and go on this list. I'm going to go into the one that is the TF. You see here TF. So now select that one, open, and there are a bunch of things appear here on the robot. So let me get close to it. Great. So those are all the frames that exist in the robot. You can see there are a lot for each wheel, for the LiDAR, for the camera, for the center of the robot. Let me do one thing. If I want to remove one of the displays, I can just unclick here, and then it will disappear. It should. Yeah, there it goes. So now we can see, we don't see the robot model there, and then it's easier to see the displays. But we can do more things. For example, on the TF, if I open the configuration, I can see here the marker scale. I can make the marker scale smaller, for example, half, and then I can see them smaller. It's easier. And then it's easier to understand. Also, I can add the names. So here there is an option that says show names. Then I can click on here and get all the names. Yeah, there's a bunch of them. It's too much. But you can use this for debugging and see if the proper frames with the proper names, they have been set properly. And if you go here to the frames option, it says all enabled. Then you can remove that all enabled, and then you can be adding only the ones that you want to check with the proper name and so on. So you have more control on what you display here and check one by one or 2 by 2, it depends on what you want. Body link, for example, is here. Then let me see, I'm going to add the base link. I want to add the base link, the one that we selected as the central feature frame. Okay, so base link, you see, it's at the center of the robot, projected over the ground. So that's the base link. And this is the frame. All those are frames that exist currently in the ROS program that we are running, that is for the simulation for this robot. And then this fixed frame, the one that we select here, is from which one of those frames we are representing the information. For example, now we are representing from base link the LiDAR. But if you change and select another one, you will see, let me get out of this here. So if I get an overview over the top, now I'm going to select, let's say, for example, I'm going to say the right wheel. Okay, I'm going to activate the right wheel. Is there? The right wheel is this one here. So now I'm going to get out, zoom out, and then I'm going to select the fixed frame as the wheel. So I'm going to select the right wheel here. So now the data, you can see there is like a kind of jump, and then the data of the LiDAR now is being represented from that frame, from that point of view, from the point of view of this frame. And this frame, the right rear wheel frame, it's located at the center of the image. And everything else is represented from that in reference to that frame. Well, you are going to learn more about this on the next lesson. Okay, so this is just a small example about how it works. So let me go back to put the base link, because it's the typical one. We want to represent the data from the center of the robot, which is the base link. Great, let's continue now. So we have shown the module, the LiDAR, the frame. So let's learn how to visualize also the camera information. And for that, we are going to add a new display, which is by topic, and it's called is the camera color image. So let's go and let's do it here. I'm going to collapse this TF. I'm going to show again the model of the robot. Now I'm going to add a new visualizer by topic, and then on camera, it's camera color image raw. Let's open this, and then here there are 3 options. Let's select the image. So now this image here should show, yes, after a while. So start receiving the image that the robot is seeing in its perspective on the simulation, right? So now you can see that the camera is, what the robot is perceiving with the camera is seen here. If you move the robot around, you can see if this camera is properly working, if it is detecting what it is, what is the delay, etc., etc. So that's how you would do to work with RBase in order to visualize all the important information that you need for your robot to check that everything is correct. Then that has been quite a lot of work to configure all those things in RBase. So the next time, maybe when you start, it will be a pain to start doing this again every time. So because of that, there is a very handful option here on the menu file, which is Save Config As. And then if you click there, you can select that directory on your workspace. Let's see, let's go to the home user and then put here a name for that file and then configure, for example, configuration, I don't know, whatever the name that you want. So now if you go to the IDE files, you will see that it exists this new RBase file. And then next time that you launch RBase, you can load directly this file in the same option on File, Open Config, and then you will see our configuration RBase file, and then everything will be set up for you automatically, so you don't have to be doing all this job. Here on the IDE, you can see that the file has been saved as configuration RBase. Yes, it contains all the configuration. Okay, so let me see if something more. Okay, yes, I want to clarify one thing that gets into confusion to many people is that RBase is the simulation of the robot, right? Because, why? Because it looked like a simulation here, but it is not. You cannot confuse the simulation here with the RBase. This is a very important concept. Unless you understand the differences between the simulation and RBase, you are going to get confused those ideas in your mind, and you will not understand the real value of RBase and how much can help you into debugging your ROS programs. This simulation is like if I had this robot here on my side, the real one, but I don't have it, okay? I don't have this robot because I didn't buy, because whatever. So I use the simulation for making like a way of having the robot and doing experiments in the computer. Okay, you consider simulation like this, like the real robot. We can consider like the real robot. Then, what we have with RBase is a visualization of what the ROS programs think that the robot is providing. So that's why you can use RBase to see where there are some errors in the programs of ROS. For example, there is a program that is publishing the model of the robot based on a URDF file. You will learn this in the future, okay? So if the model here that appears is wrong, it means that ROS system thinks that this robot model is in another way, in the way that appears here. So maybe your simulation looks correct, but this looks incorrect, because those are two different things. The simulation is the real robot, and the RBase model that appears here is what ROS thinks is the model. If this one is not the same as in the simulation, then there is a problem. So the laser data, for example, the laser data is what ROS systems are publishing based on what the real robot is detecting. If what you see here doesn't match what it should based on the reality, on the simulation in this case, then there is some problem there also. So the RBase is just representing what ROS thinks that is the data that is coming to its programs. If this data is wrong, then the programs will not work properly. So that's why we use RBase to debug programs. Okay, then there is a lot more about ROS debugging tools. For instance, you can also add debugging messages that appear in different colors, that you can filter, that you can check only one specific specific conditions. So all this messaging that you can add to your code in order to debug where there is a problem, that's also something that ROS provides special. There is also a way of visualizing the tree of frames. So here you have seen all the frames of the robot, but you cannot see very clear the relation between them, if they are connected or not. Then if there is no connection between one frame or another, then there could not be a transformation between one frame or another. So you need to see the proper connection between the frames in a graphical way. So that's, for example, another tool for debugging. Also, you can record and replay logs in ROS by using ROS bags. That's another tool that it has. And many more, okay, many more. So I don't have the time to do all this in the crash course. I taught you the most important one, which is RBase. That's the most important one. And if you want to take more, then you can take the ROS2 Basics in 5 days course and then learn more about all those tools that are here included. Okay, so that's okay for this lesson. Let's go to the next one. Great, let's start the next section of this ROS2 Jazzy Crash Course of 2025 about robot frames and transformations in ROS2. Remember that if you don't have this project open yet, and you don't have a copy, you can get into the link that we have here below this video and get a copy of the project. Then the project, once you click on that link, you will get a copy and it will appear on your account at the construct under the My Project sections. So you will have a project like this copied on this area, and then the only thing that you need to do is to run, and then it automatically will pop up this screen with the notebook. It's open that contains all the instructions of this course. Okay, so let's go down into the notebook and select the part 4, robot frames and transformations in ROS2. Right, so what is this about? This is a very important subject in ROS, and you need to understand. But it's also a very important subject in robotics. So that's why I'm going to start right now delivering some introduction into frames, into transformation basics. Okay, so let's imagine that we have this typical robot problem with a robot which is located here, and then on his left side there is this rock in the middle. Okay, that's the problem that we have to know. Then what we want to know is about the coordinates of each one of the parts, but with respect to what? Yes, so that's the problem of the frames. You need to have a frame that says is measuring from this frame, the distance of the rock is this one. From this frame, the distance of the robot is this one. For example, we can say the frame of the robot. So we have a frame of on the robot, and then we can say from the robot frame, the rock is located at 1, 2, 3 meters to the left hand side, right? So that's the thing. So that's the coordinate frames. And that's an example of here. That will be the robot that is here located. And then we have 1, 2, 3. This is the rock. And then the center of the rock will be in the 4, right? And then, well, so that's another, that will be the x-axis. But this rock is only located on the y-axis. So here we are mentioning very important thing, which is the direction to which the robot is looking. So in this case, the robot is looking into this direction. From top view is looking into that direction. So that is the x-axis that you know. And then the left-hand side of the robot, it is the y-axis. Right? So you can see very clearly in this picture. So this is a convention that is used in robotics, and you have to follow always. So in a 2D environment like this, then the rock will be, the center of the rock will be located at 0x and 4y, right? That's the coordinates based on the frame that is located at the robot position, based from the robot position, right? So now, let's continue by increasing in one dimension this frame, instead of having 2 dimensions, now we have 3. Which one is the 3? Is the height. Then the height is called the Z axis, and it's going from the bottom to the top of the robot. That's very clear. So in this case, the center, let's say the center of the rock will be at 0, 4, 0, let's say, on the base of the robot, of the rock. At the base of the rock will be at 0 height. If we want to measure this other part of the top, that will have like 1, 2 meters in Z. I don't know. It depends on the height of the robot, right? But you get the idea. So that is the concept of the frame that measures distances based on that frame, taking this frame as of reference. Okay, this is very, very important. Stay with me and you are going to understand more in a minute. Then, this frame that we are locating here on the robot itself, we call it a local frame because it's local to the robot. To the robot, it's very important to know where are the obstacles, where are the things related to itself. Okay, and then the robot can say, oh, there is a rock on my left at 4 meters. And that's very interesting for the robot itself. But that measurement is not useful for any other robot that is around there. It's not useful for any other person because the other robots, the other person will be in other locations. So saying this robot that in its frame there is an obstacle of 4 meters doesn't provide any distance of the obstacles to other people, other robots. For that, we need to have a global coordinate frame. A global coordinate frame is like a frame that all the elements in the scene are sharing. So this global frame will be the one that is, when you say some distance based on that global frame, then all the robots that are in that scene, all the people that are in that scene, they will understand where is the obstacle because it's a frame that all of them share. That's why we call it global. In the local coordinate frames, when we have a robot, in a robot we have several frames. It depends on the different parts of the robot. We are going to see that in a minute, and actually you saw already something on the previous lesson when we were talking about orbits some minutes ago in this video itself, right? Then in this case, so the robot itself has several local frames, like the head frame. So this is very interesting because the head frame, when you detect an obstacle based on the vision of the robot, that is, the camera is at the head frame, then the distances are only from the camera of the robot. So they are measured from that frame. But that doesn't mean that the center of the robot is the same distance to that object that the camera is detecting. So some transformations from the obstacles detected on the head frame need to be performed if we want to know the distance of an object related to the base of the robot, for example, or for the arm of the robot. So the camera, the head knows that there is an obstacle 1 meter at the front of the camera. That means in the x-axis, 1 meter, then 0 in z, and 0 in y, right? But then for the arm located around here, then what about that? So the arm is in another different location from that frame. So you need to do those transformations from the head frame to the arm frame, wherever it is, in order to understand from the arm where the hand has to go and grasp. Okay, so all those are transformations between local frames. But in ROS, actually, we don't make a difference between transformations between local and global frame as long as they are connected. So if they are connected, so that means that there is a transformation between one frame and another. That's when they are connected. For example, in this case, there is a transformation between the neck frame and the head frame. And what is the transformation? Well, that's defined by the URDF, by the shape of the robot. By the shape of the robot, because this is kind of fixed, right? This cannot be moved. It's fixed on the robot. So if you know the dimensions of the robot, you know how to transform one coordinate from one frame to the other. And that's a connection. That's what it means, the connection. That there is a transformation and that this transformation is known. So those transformations in robotics, they are managed by using very complex matrices operations. I mean, there are a lot of operations that you need to do in matrices, but in ROS, there is something that is called the TF. And then the TF is the system that computes these transformations automatically for you. And that is so huge advantage. You can have at any moment in time all the transformation between all the frames, and you can transform like this, one distance from one frame to another that interests you for your application. Okay, so let me go. Yes, so here is about the conventions on the robot that follow the right-hand rule, as you already know about this. So looking to the front of the robot that we have in our simulation, this is the red one, is the x-axis. To the left, as I mentioned, is the green axis, is the y, and then to the up is the z-axis. So based on that, you know how to use the coordinates. When somebody says one coordinate related to the center, to the base link of the robot, then you know about that. Where related to the robot, where is the obstacle? Well, this convention is applied to all robotics. Okay, it's not only for ROS, it's for all robotics, and then also for cars. So in a car, you will see something like that: X, Y, and Z. For a drone, the same thing: X, Y, and Z. So X, remember, is the direction that usually the robot is facing. Is where the face of the robot is, wherever you define that face, okay? So it depends on the robot. In the car is very clear. In this robot also is very clear. In this drone is not that clear, so you need to decide. I mean, the creator of the drone. But the same applies to all of them. Okay, so now, let me show you one utility that is provided by the transformation, the TF package of ROS, that is very useful. Okay, so how to create a coordinate frame which is between two elements, how to do a transformation. And let me show you here, for example. So here, we could do a transformation between the base of the robot and the rock. Okay, and then we can create another transformation on the base of the rock by publishing this transfer, how to transform from this center of the rock to the center of the robot. But this is, in this case, if the robot is static, is not moving, then that will be easy because you compute this. The problem is when the robot is moving around. So in this case, what we are going to see is how to do this kind of static transformations for frames that are not moving. Okay, so for example, let me tell you one of the frames that are automatically launched, created when you launch a robot into a simulation, which is the odometry frame. The odometry frame is the frame that we are going to visualize in a minute. The odometry frame is the frame that it's started. The origin of that frame in the area is the starting location of the robot. So let me show you this in a minute by launching the simulation. So let's go on, let's launch the simulation with this command that I have put it here again. And then let's visualize those frames in RBase, and then that will be easier to understand. So let's launch the simulation first, copy the command, and let's open a terminal and paste the command. There it goes. So now the simulation is opening here. Let me put it full screen in this area. And here we have our robot. I'm going to get close. Yeah, I always do it the other way around. Yeah, and then I'm going to turn it a little bit with this button. I think it is, yeah. So I'm going to rotate a little bit so we can see the robot and we can see the door here because I want to talk about the door. Then here the simulation has started and then the robot has just spawned here. So imagine the equivalent will be having this robot, real one, then you switch it on your location, wherever it is, at your home, at your office, you switch the real robot. So wherever the robot has started, that is considered the Adam frame of the robot. The Adam frame is the frame in which the movement of the robot is being measured by computing odometry. Okay, so I suppose that you know what is odometry. If you don't, then don't worry. Odometry are just the calculations, internal calculations that the robot is doing of what it thinks that has moved from the initial location. So when you switch it on, then the robot starts computing this odometry, how much it thinks it has moved. And then this measure has many errors, and because the robot is limited, okay? So that's why we need some more sophisticated systems than odometry like SLAM localization algorithms. But that's not the point here. So here we have this Adam frame. And the Adam frame is a global frame. It's not a local frame. So it's not a frame that is traveling with the robot. That's what a local frame means. It's a frame that it's only for the robot itself. And as such, when the robot is moving around, then the frames that are local are moving with it. So the local frames, they only are useful for the robot itself, not for other people outside, in general. Okay? In general. So this odometry is being set automatically by ROS at the location where the robot is switched on the first time. So now here, where the robot is, we have a frame that is called Adam. And we can see that. So let's see. How do we see those frames? You already know, because I explained you on the previous lesson. It's by using RBIS. Yes, you said properly. So in order to launch RBIS, we are going to launch by using these two commands. Remember that the first one is only necessary in this case because we are using this robot, specific robot, and we have its model installed in this simulation workspace. I don't want to go into details of that because it's going to generate more confusion, but just mentioning in case that you are worried. So in order to launch RBIS, we launch ROS2 command, and that is going to launch the RBIS. Then, okay, yeah, so I have already, let me switch it off because I already have everything here set up. So I thought that I had deleted all of them. So I'm going to remove this, then remove this, and I'm going to start from what it usually starts. It starts with map. Okay, so that's how it starts usually. Now, we have this system, this RBIS visualization, we can see nothing because the fixed frame is one frame from which everything is going to be represented on the scene. Okay, and then this map frame doesn't exist. Map frame is a global frame. It's a frame that is used when we are doing navigation, when we are using localization systems like SLAM or AMCL or any other, in order to identify where in the area is the robot or other parts in a global way. So any other element, any other robot person can know where the robot is. So it's a measure that is global map. But nobody is publishing this. So nobody is saying in the frame map where is the robot, because we don't have a localization system in this example. So the one that we have are the one frames that we have are the ones that appear on this. When you click on the drop-down menu, the ones that appear here. And then we are going to select autumn. Okay, we can select autumn, right? And then nothing appears, right? Yet, yeah, no problem, because still we need to add visualization, displays, visualizers, displays. So let's add a display. Click on the add button and then go on display type, go to the bottom and select the TF. Now we can see those are all the frames that exist in this robot, actually in this scene, in this simulation, in this environment. Only the ones that are local to the robot. Only those? No, there is also the autumn that is mixed here because the robot is located at the same location. So if you open here on the TF, all the details, then you click on show names, we are going to see the names. Okay. Then on frames, instead of clicking, remove the click of all enabled, and then now let's go and click on autumn. And there it is. So you can see that the robot, this is the autumn frame, which is global. And then the center of the robot, usually it's on base link, so we can click also on base link. And what happens? That both of them, they are at the same location. Yeah, that makes sense. Because the robot has started at that location and has not moved, so the center of the robot is at the location of the autumn frame where it starts. That's by definition. Okay, so the base of the center of the robot is where the autumn frame is located when you switch it on. So that is correct. Now you can also include some others, like for example, where is the laser? So it's on the top and it's looking backwards for some reason. I don't know why. Okay, so it's on the top of the robot. Then let me show you something else, which is about adding a new display, which is the robot model. So select add, then go on the list display type, select robot model, okay. And then now should appear below. Now we have to go down again, open the robot model options, as you know, and then where it says description topic, select by topic, description topic, sorry, I clicked on the wrong one, robot description, yeah. And there it is. So you know all this that I am showing you, you already know from the previous lesson. But now I'm going to change the alpha a little bit. So I'm going to put 0.5. So we can see both things, the model and the frames. I'm going to remove the laser because it's just. But as you can see, the laser frame is at the location of the laser. So you can see that it's properly set. Right? It's at the center of the laser. So it's correct. And this is where I'm going to remove it again. This is where the robot base is and the autumn is. So now, what happens if we move the robot? So if we move the robot, what we should see is that the base is moving away from the autumn, and then the autumn remains at the center. Why? Because the autumn is the fixed frame. It's the frame that doesn't move, and is from which we are representing all the rest. But more interesting than that, there is a transformation between the autumn frame and the base link. So let's move the robot and let's see. So the command to move the robot, I have put it down. So here is all the explanations that I have explained already, with images, how to select, and some extra markers and data. So you can see here the details with all the names, and so this is the same thing. Okay, so now let's go and select this command, which is for moving the robot. Copy the command, let's go to the terminal, open a new terminal, a new tab, and then paste it. So now, if we move the robot, let me get a little bit out, and now I'm going to move the robot forward a little bit. Okay, there it goes. Okay, so now you can see that the odometry frame is staying fixed there, and then the base link, which is the center of the robot, goes wherever it is the robot, and that there is a connection between them. Yes, this connection represents the transformation between odom and base link. And what is the meaning of this? The meaning is that you can always know from the odom frame where is the robot. So the odom frame, that's what I started this lesson by telling you, from this frame to the front, whatever, to the left, whatever, to the up, whatever. So in this case, the odometry should say, like, the robot is, let's move it a meter. For example, a meter, each square here is a meter. So let me move it a little bit more. So we are at almost a meter. Let's say that is in a meter right now, more or less. More or less, okay, this is just to get the idea. So we can see that the frame, this frame is, the base link is almost at a meter line. So I will take it like this. Then now let's do one thing, and let's practice your previous knowledge of ROS topics. So let's open another tab, and then let's type ROS2 topic echo of odom. Switch the keyboard because it's getting strong. Okay, is odom. That is the topic, odom. So there is a frame called odom and there is a topic called odom. Those are two different things with the same name. Okay, so don't get confused. So what I'm getting now is listening to the data. Okay, it's not called odom. Okay, let me ROS2 topic list. Maybe I confused the name, okay, of the odom. Let me see. Oh, yeah. Okay, sorry. It's ROSbot XL base controller odom. Okay, no problem. Let's repeat the process again. ROS2 topic echo of this one. And there we go. Control C, because I want to know. So here is the covariance. We don't need the twist also. But what we need is this, the position and the pose. You can see that the base link related to the odom, that's what this means. Odom, base link related to the odom is at position x 0.98, x0 and z0. Yeah, and this is the orientation. That is a quaternion. You cannot know, but this means 0. So it has not rotated anything. And that's exactly what is happening here, as you can see. So the data is correct. Then we are using the odom frame as a global frame in order to make a transformation to the local frame of the robot. And by doing this, we are able to know where the robot is from a global frame. Now, let me continue to the part that I wanted to teach you about the static transformations. So if there is something that is fixed from a location that you know that is going to stay there forever, you can provide this transformation so it can be used later for some other things. For example, in this case, what we are going to do, let me show you with an example. In the simulation, we have in this simulation, we have, where is the robot? Yeah, the robot is moved forward, so we cannot see. Yeah, there he goes. Yes. So here is the robot. And there is this door. Then the door is fixed, is there. So we can publish one transformation from the frame of Odom that was around here, where the robot started, and indicate that it's about 5 meters behind the Odom frame. So we can say that the door is at that situation, at that place, forever. And then how do we do that in ROS? By using this command, which is ROS static transform publisher. So with this command that you can see here, we can express those transformations that are fixed in the environment for whatever the reason. Then how do we express? By expressing the X, the Y, the Z, the roll, pitch, yaw. That means the different rotations, and from which frame to which new frame. So we are going to create a frame at the position of the door. It's a frame that we are going to call outdoor. Okay. And then this outdoor, we are going to indicate that is from the Odom frame is 5 meters, more or less. I don't know exactly. I didn't measure. It doesn't matter. 5 meters behind on this frame. What does it mean behind? It means that is on the x-axis behind, and that means -5. So that's why here on the x value, I'm indicating -5. Then y is 0, because the center of the door is more or less at the center, at the same position of the center of the frame Odom. And the z also, because we are measuring at the base. And then there is no rotation, so all those values 0. Okay, so now let's do it. Let's publish this transformation. So remember that the transformations, they need to be published on a periodical way. So it's not just once and then it's there, because these computations of transformation, they are continuously being computed in the background. So they need to have the updated data in case that something changes. So it's being updated all the time. So we need to open a terminal and publish the transformation in the terminal. And then we see this, that it's being published. Now it says, I am published. So as long as this is not Control-C, this will be spinning the transformation as it says until it is stopped. So now we have this transformation from the frame Odom to the outdoor frame. And what can we see on RBase? If we go to RBase, we can see now that, okay, let me see, I can put it here. Then now a new transformation has appeared and a new frame. You see from Odom, if we go back 5 meters, yes, we can see the outdoor transformation. That is the one that we are publishing now. If we stop, so let me show you here, very convenient way. So let me put it here. Then let me close, do a Control-C. So you will see what happens. So if you do a Control-C, then this transformation stops being published, and then RBase is still getting it because it receives a lot, and also the TF is starting to vanish. Slowly is going to vanish until the transformation disappears. It takes a few seconds. What I wanted to show you is about this static transformation that you can publish, and how it is. It has to depend on another frame that is not moving. You cannot publish this static transformation related to the base link of the robot, because if the robot moves, then this transformation will not be updated because it's static. It's a fixed transformation. It's always the same transformation. And if the robot moves, that transformation is not correct. So that is why this is only valid for things that are fixed in the environment somehow. For example, inside the robot itself. So all those transformations that you have in the robot, they are most of them, they are static, except the ones of the wheels that are rotating. But the rest of the things, the rest of the frames, the laser related to the base is always fixed because the robot is not doesn't have moving parts except for the wheels. That's why they are fixed. And your next question should be, so how all those frames from the robot came from? Well, this came from the URDF of the robot. So if you have a URDF model of the robot, then you get the shape of the robot. And this shape of the robot is specified in a file that is called URDF, in URDF format. And then this file is the one that defines how the different parts of the robot get connected to each other. And this has been provided to you in this example. That's why we can visualize all the frames of the robot. But if you want to know how to create the URDF files for your own robot, then I recommend you to check this course that we have, where we explain step by step how to do it and all the tags that you need to know in order to properly set the structure of your robot so it can be understood by ROS, and then the transformations can be computed automatically for you. Okay, then what else? Yes, I think that I have covered everything so far, but there are a lot of other things to learn about TF. So this is just the peak. It's just a crash course, as you know. Then if you want to learn more about TF, everything deep, then check also this other course that we have about TF, where you are going to learn everything. Like, for example, in this case, we have published this transformation on a terminal. But how would you do that if you want to do it inside a program or inside a launch file? So you don't have to be typing when you open your robot. You don't have to be typing those transformations. And also how to publish dynamic transformations. So things that are moving at the same time that the transformation is being updated based on those movements, for example. So all those things, they are covered in this course, and many more things. So there are a lot of things that you should know about ROS and transformations. This is just an introduction so you understand the basic concepts. Okay, so that's all about transformations. Let's go with the next lesson. And now let's go for the final lesson of this crash course, which is about DDS. So remember to open your project for this lesson. If you have already copied the project, then you will have it here on the section that is My Projects. So we'll have a copy here of the project. If you didn't have still a copy, you can go on the links below that we have on the video, and then you will find the link, click on the link, and then you will get this copy. Once you have the copy, just press Run. On My Projects area, press Run, and then the project will open like this. Okay, so now the notebook will open automatically, and for this session, we have to go to part 5, Introduction to DDS. So if you click there, the new notebook will appear, which is about the DDS. And remember that we have this command to launch the simulation. In case that you don't have the simulation running, you can launch it right now. So let's go, let's copy the command, and then go to the desktop again. Let's open a terminal, and then launch the command, paste the command on the terminal. You know how it works already. And then the simulation is going to appear automatically here. Great. So let's continue while the simulation is running. So what is DDS? Is DDS the same as ROS? Why do we have this DDS here? Okay, it is very important that you understand how it works, because then later may have some problems in ROS programs communicating between them, and you will not know what it's about. Then DDS could be the cause of some of those problems. So you need to understand how it works very well. Then here in this image, we have an image showing the architecture of a ROS2 system. And then it starts at the top by the ROS application. This could be the navigation system or the moving system for moving arms, robotic arms. So that would be this layer. Then here in this layer, we have the libraries that allow us to create those applications with ROS commands, with ROS procedures, with the framework of ROS. But then, how do all those applications communicate between themselves? How do the topics work? How they can connect? This is by using DDS. So DDS is the protocol that is used in order to communicate all the nodes, all the topics, the publisher, subscriber, services, etc., underneath ROS. Okay, so DDS is on this layer that we have here, DDS implementation layer. You can see there are several types of implementations. So basically, those are companies, different companies that implement DDS in their way, and you can use any of them to communicate. You can use any of them. In ROS1, we don't have DDS. We have TCP communication already embedded. So it's the typical TCP communication. So you don't have to switch the implementation. But in ROS2, there is a possibility to change the DDS implementation. So for now, don't worry about that. So in order to use the DDS implementation, ROS uses the ROS middleware interface to communicate the ROS client libraries with the DDS. So the application goes like this. So you have the ROS application at this layer, which uses the ROS libraries in order to create ROS applications. And then in order to communicate the ROS nodes, you need to use the middleware to connect to DDS, and then DDS does all the communication between the nodes. So that would be the system, how it works. Then DDS is being used in ROS2 because those 4 characteristics that it has. First one is data centricity, which means that DDS is putting the attention into the transmission of the data. So that's like the main goal, and that's very, very important. And it's trying to do this transportation of the data with a minimum amount of impact on the system, on using the system, and also with a low latency. So then it contains several implemented functionalities inside in order to achieve this. Like, for example, when to decide where to publish the information. For example, in case that you have a topic that nobody is subscribed to, and then instead of being publishing all the time, then DDS may decide to stop it because there is nobody listening to this, and it's a waste of resources and that. So that happened in ROS1, but then here in ROS2, this is managed. And many other functionalities also that are related to transmitting the data. So this is one of the functionalities of DDS. Another one is the QoS. That means quality of service. So with DDS now in the ROS topics or communications, we can specify different qualities for the messages. That means we can specify, for example, that the messages, they have to be receive and acknowledge reception for every message for this topic. Or, for example, we can say, no, it's not important. We just send the messages, and the ones that arrive, it's okay. The ones that doesn't, it's also okay, for example. And then some other qualities, this is called qualities of service, and you can configure in this way the different topics. Is very useful. For example, in situations where the communication between the robot and the external computer is not reliable, because it's occluded or whatever, those situations. So there is where the quality of service is very important. Then also another capability is the dynamic discovery of DDS that allows ROS to not need to have a ROS core. Because of this capability, then ROS is able to discover the other nodes on the spot as they are executed. This has some other problems, okay, but for now it's very, very good. And then finally, it provides security, because in ROS1 we have this problem that anybody that gets into the network can check the topics, can send commands to the wheels and all those things. With DDS, there is implemented security where you can hide all that information, and then nobody that is not certified to look for those topics or send commands, it's going to be able to do it. So those are like the basic characteristics why DDS has been introduced into ROS2. So now we have ROS2, which is a more mature and more professional system for robots, middleware for robots. Then here in this section is about checking which one is the current middleware. As I mentioned before here on the list, this DDS is just a specification. So some people in the world, they said, hey, we are going to do this protocol of communication and it has to follow these rules, okay? They specify the rules, but then how you implement those rules into actual code, this is something different. So this is something that anybody can do, because they read the specification and then implement. So those are the examples that we have here. So here, Proxima company has implemented the fast DDS. This is one. Eclipse has implemented Cyclone, and RTI has implemented Connects. And you can implement yours if you want, okay? No problem. But so far, those three are the mainly available for ROS2. And then you can check in your system which one is the one that is running at present. And so let's do that. Let's copy the source command into a terminal. So in this terminal, I'll launch the simulation that is already here. Great. Then let's go to the implementation. So let me paste the source. And then the other command, this command is ROS2 Doctor. ROS2 Doctor is a tool that provides ROS2 in order to know a lot of information in ROS. If you want to know more about this, you can check our ROS2 Basics course where we explain about this tool. So here you see there is a lot of information, but the one that we are interested in today here is for this one, RMW middleware, and it says Fast RTPS, CPP. Great. So that's the one that is running in this system. This system is, as you know, because of the name of this course, is Jazzy, ROS2 Jazzy. Then by default, when you install ROS2 Jazzy, you get fast DDS as the DDS implementation. Okay, here you can see that it says fast RTPS, but fast RTPS, fast DDS is the same thing. Just the company was changing the names at some point in time, and then so this get replicated there. Yes. Okay, so that's the one that comes by default when you install DDS. When you install ROS2. Great. But it can be changed, okay? We are going to see in a minute how to change this. Then about something else that I want to explain is about the Xeno. So Xeno, it's another communication protocol for ROS systems that has appeared in the last couple of years. And this Xeno is trying to solve, among other things, is trying to solve the problem of communicating systems, ROS2 systems that are in different computers and that are communicated by Wi-Fi or through the internet. So we have this ROS2 system that is the host number one, and then it communicates through Wi-Fi or through the internet directly with another host, which is somewhere else. And then also it's running a ROS2 system, and they want to share information and so on. So DDS it's not good at managing those situations, because DDS was not meant for this kind of situations. Then we have this problem of communicating. Then for that, it exists Xeno that allows this by doing a kind of a bridge, and allows to jump through all those networks and communicate efficiently in ROS2. I'm not going to explain you more about this, about Xeno. If you want to know more about Xeno and all the options of DDS, many details, I highly recommend you this DDS for Robotics course that we have created, and that contains a lot of details, and also you have a lot of practice in order to figure out errors, because that's the main problem with DDS, that when you have an error, it's very difficult to debug, and we are dealing with this in this course. Then let me tell you about the different implementations. You need to install them on the system. So in this case, the FastStart TPS has been already installed by default. Then here we have put the commands that you need to use in order to install the different ROS packages with the different DDS implementations. So here, this is for you. Then now, once they have been installed, how you can change the DDS implementation in your system. So it's very easy. It's very simple. You only need to set one variable that is called RMW implementation. It's a system variable, it's a Linux variable of the system, and then by setting them to any of those values that you have here on the notebook, then by setting that, you will be changing the DDS that is used on this terminal that you are setting this variable. Okay, so how will you do it? For example, you want to run your package, your application, then you export this before launching your application, and then that's it. That's it. We are going to see that in a minute, how to do it, and we are going to do it. But before that, let me explain you about another thing of ROS2 and DDS related, which is the daemon. So whenever you change the RMW implementation, we recommend you that you stop the ROS2 daemon first and then start it again. So for example, let's execute this command in our terminal. So it's ROS2 daemon stop, then ROS2 daemon start, and then we are going to check for the RMW implementation. So let's do it on a terminal, and you are going to see what happens, okay? So if I launch it, now it's stopping the daemon and starting again, and then I do this command that what it says is, give me a list of all the processes and just show me from that list only the one that is talking about the RMW implementation. And here you can see that the process that appear, if you read the whole line, then it's called the ROS2 daemon. Okay, so that's the name of the application that is talking about RMW implementation. And which one RMW implementation? The fast DDS one. Okay, so that's telling us that the ROS2 daemon that has started is starting with this DDS implementation. Okay, so now you can understand when the daemon is working in one implementation or another. But what is the daemon? Okay, so the daemon is it's a tool, okay, that has been implemented for ROS2. It's a kind of ROS core, but it's not. Okay, so it's not a ROS core because there is no ROS core in ROS2. But the daemon is a tool that whenever you launch a command that is on the terminal about topics, services, or whatever, that you are asking for information about the topics, the name of the list of the topics, the information about that specific topics, the echo, and so on, then this ROS2 daemon is going to start automatically and start capturing all the information about the ROS environment that exists. So which nodes, which topics exist, and all this data and store into an internal database. So the next time that you are asking, all this information is already fresh, and then it can deliver this faster. then when you change the implementation, yes, this ROS2 daemon can be affected by that. So in most of the cases, it's not going to happen anything, it's okay, but in some other cases, changing the RMW implementation and not stopping the daemon can produce some errors, communication errors. That's why whenever you change the RMW implementation, we recommend you that you stop the daemon and then start again. Then in this case, so how can you check if your daemon is running? Well, you can check if the daemon is running by using this command, phps. Okay, this command is telling you if the daemon is running or not. Then there are other ways. For example, if we launch the ROS2 daemon status command, let's go on the terminal. Then it says the daemon is running. Then if I stop it, then I can say daemon status and says the daemon is not running, of course. But also if I launch the psf command to list, then it doesn't appear. Okay, the process doesn't appear anyway. So those are two ways of checking for the status of the daemon. And yeah, so you can see, for example, this command is very interesting because now we have stopped the daemon. And then if we I have launched so if I do this command that is the ps, well, it's not going to say anything. Let me copy and launch it. So it's going to appear nothing. Yeah, only the command itself. Okay, so that's, if you understand Linux, you know that there is nothing about ROS2 daemon. Then we do a ROS2 topic list, and then you will see ROS2 topic list. So now it says the list of topics, but what happened is what I mentioned before, is that whenever you launch a command that is asking for information about the topics, the services, etc., automatically the ROS system is launching the daemon. So if I now execute the same command, ROS2 daemon, this one about, yes, so ROS2 daemon. What? Oh, yeah, sorry, there is a mistake here. I see. It has to be like that. Okay. Yes, so there is a mistake on the notebook. So I am correcting the mistake here automatically right now. So you don't have to, when you copy this project, you don't have it. Because I'm doing the video, I'm modifying this. Okay, great. So let me do it again, okay? Because initially it was wrong also. So let's stop the daemon. Now let's go and do a PS to check there is no. Okay, then let's do a ROS topic list. Get the list, then the ROS2 daemon has started automatically. So if I do a PS again, it appears here. Okay, yes. Okay, so that's what ROS2 daemon is working. So you don't have to launch it. It will automatically launch when you request any information about the topics. But if you want to have control, you can stop it and start it again whenever you want. And that's what we recommend that you do whenever you change the RMW implementation. Okay, so for example, let's do this command here that is setting to fast RTPS, then stopping the daemon, starting again, and asking for the implementation. Okay. Yeah, so I know it's a very simple command. You know what is going to happen. It's going to show that it has RMW fast RTPS implementation. Okay, yeah, because actually we didn't change anything here. We already were using this one, so no problem. No, it has done nothing because we didn't change anything. But now if we do the same command, but now we change to cyclone DDS. So let's do the same set of commands, but changing into Cyclone DDS, so you copy and paste here. So now we are going to see that the RNW implementation has changed to Cyclone DDS, right? And then we stop it. First we change it, then we stop the daemon, then start it again, and then ask for this. Okay, so far so good. Then now let's do a small test, okay? Just a very small test. Let's launch a talker and a listener with fast RTPS, and then go the same example with Cyclone DDS, and let's see what happens. What is happening there? What are the differences? So first, in one terminal, let's go copy here, and I'm going to launch here this command that what it does is setting, let me see, is, well, first it's going to a specific directory and sourcing it, then it's setting the RMW implementation into fast RTPS, and then launching the talker. There it goes. So let me change here the name, and then instead of that, I'm going to put talker, so it's easier to understand. And then here I'm going to launch the listener. Great. So that's the other example. So the second code. So it's setting the implementation to fast RTPS and launching the listener. So let me copy the full command and launch it here. There it goes. So now this listener is listening to what the talker is saying. And then we can see that the messages are sent and then received on the other side. You see more or less the same numbers, 49, then 50, 51, and so on. Right? Great. Then, so what was the problem? No problem. So this is working. Okay. So now let's do the same thing, but with another export for Cyclone, and let's see the differences. You will see. So let's go. I'm killing those. And now I'm going to launch again the talker with changing to Cyclone DDS. Okay, there it goes. So now Cyclone DDS has been changed. Launch the talker and go to the listener and do the same thing. And then you can see that 13, 14, 15, 16, 16, 17, 18. Okay. Yeah, the same. Yes. Yes, that's expected. Yeah. Why? Yeah, because they are just different implementations of the same instructions. So DDS is a set of instructions that were decided by very intelligent guys. They said the communication should be this way. Now you implement it to code. And then here we can see both of them, they work. Okay, so no problem. Okay, this is an example, a simple example. But I can tell you that there are some minor differences. I have put here some of them. For example, FastDDS gives access to some extra quality of service profiles and configurations that Cyclone doesn't. So for some specific projects, you may need those extra QoS. Then Cyclone is better with users that already have Cyclone DDS apps outside ROS2. So they are more compatible. Then there are some events that are not supported in some of the implementations, in FastDDS or in Cyclone. So those are very, very specific. And in practice, what we have found in general in the community that some stacks like Navigation, MoveIt, and OpenRMF, they were better with Cyclone in local setups, local. When you go outside in different computers, in different networks and so on, then it doesn't. So but this is changing all the time, okay? So this is at the present, but maybe when you watch this, things have changed. So yeah, it depends on your situation. Then the good thing is that to change from one to another is very easy. So if it doesn't work with one, you can change to the others. You can try any of the others. Then I haven't tried very much the Connex DDS, so that's why I'm not talking a lot, but this is another opportunity. You can try and change and see what happens. You can tell me. Then what we are going to do is to create a simple publisher and subscriber to test the DDS, and then we are going to do some measurements, real measurements, and you are going to see a little bit of differences. Okay, even if they don't matter that much, but then you can see. And also, we are going to be practicing what you have been learning previously in the other lessons. Okay, so we are going to create a new package, DDS test package. Of course, it has to be, remember, on this workspace, on the ROS2 workspaces /src. Okay, remember, only there. So you know that. Here is the command. We provide the command, no big deal. But you need to understand what you are doing. Okay? And then we are going to call it, here is in Python, is a Python package. Then we are going to call it DDS test package, and the dependencies are rclpy, as you know, and standard messages. So let's go. Let's create it. We are going to create the whole application. Okay, so let's go, and let me kill those ones, the talker and the listener. So I'm killing it. Then I'm going to issue this command to create a package. First, I go to the proper directory, and then I create a package. There it goes. And now we are going to create two files, the publisher DDS and the subscriber DDS inside the test package. Okay, inside this directory that exists inside this package. Remember that in Python, ROS programs are a little bit strange. So let me open the editor and I can show you what I mean. You should know this already, okay? Because we explained it at the beginning of the session. So, of this crash course, ROS2 Crash Course 2025. So, in ROS2 workspace, we go to source, and then here we have created the DDS test package, right? Then this is the DDS test package, and then inside it, there is another directory, the DDS test package. So there you should create those files. So let's right click and create new file. One, it's called publisher DDS.py. So let's go. Publisher.py, and then another one inside there also. It's called subscriber DDS.py. Come on, stay with me. We are almost finishing this ROS2 Crash Course 2025. So let's go a little bit more. Then here is the code for the publisher. Okay, let's copy and we are going to have a look a little bit in a minute. Okay, so let's copy the code and let's put it on the file. This is for the publisher. So selecting the publisher and putting the code. There it goes. Everything okay. Then go down, and then it says the subscriber, the same thing. So copy and go to the subscriber and put it there. Yes, everything, it's okay. Great. Now, what we are doing is basically to publish some data in the publisher and then receiving the other one on the subscriber. And it's generating a unique ID for each of the messages. So, and it's generated in the time that is generated, so we can measure sometimes on the messages and how much time does it take from one place to another. Okay, but it's basically the ID is generated based on the time. So this is and then we publish the message with a publisher. There is nothing more. And then in the subscriber gets that message and then compares with the time, with the current time. And then we can see how much time is being dedicated. So this is just a parsing thing that it's getting one time, the current time, and then the time of the message, and then compute the difference. Okay, so there is no more in this code. You already know all this code from the previous part. So it's just a publisher and a subscriber. That's it. There is nothing more. And then the main, of course. Then let's go and let's create a launch file. So we have to create two, one for the publisher and another one for the subscriber. Then remember that we don't have a launch directory. Here it says how to do it in code. I'm going to, so you can copy that. I'm going to show how to do it in the other, with the IDE, which is simpler. So select the DDS test package, new folder, and then call it launch. If you prefer to do it with a terminal, you can do it with the command that I mentioned before. That is here on the notebook. Okay. Now, we have to provide, so we are going to put two more files, two launch files. Okay, first we created the launch directory, and then now we are going to create the two launch files. And actually this part, we can skip it because it's not needed, but it's to provide execution permissions. It's not needed anymore, but let me keep it like this. So this is the command. Now it's easier to do it with the terminal because it's faster. So I'm going to copy the whole command and go to a terminal and then paste it because it's creating all the files for me. So now inside the launch directory that I created, I have the two files, even if they are empty yet. We are going to populate this in a minute. So here is the launch file for the publisher that you already know how it works because it's just the package, the executable, and then, yeah, the output and so on. But this is the structure that you have seen with Alberto at the beginning of this ROS Crash Course. Okay, so nothing more to explain. Let's copy this launch file and put on the publisher. So this is for the publisher and the same file for the subscriber. Just that the subscriber is going to execute a different file. So here is the executable is the only difference between both launch files because both programs have been created inside the package, the same package, the DDS test package. So the package value of the node is the same, but the executable is different, of course, because they are different programs, right? So that's the only difference between the two launch files. Let me put it on the subscriber, which is still empty. And there it goes. Now, as you know, we need to modify the setup.py in order to create the entry points for the publisher here and for the subscriber. Those are the ones that we have specified here as an executable. Okay. So these are the modifications of the setup.py. You already saw this with Alberto. And basically it's to include the imports, then include this line for including the launch files, and then including the entry points, right? So those are the things. So I'm going to copy this completely and then go into the current setup that was created automatically when we created the package. I'm going to open and then substitute everything. So I'm going to delete so you can see. I'm deleting it and then pasting the one of the notebook that contains the two entry points and the extra line and the imports. Okay, so that's, I'm just reviewing very quickly because you already know, you have already mastered. Now, once we have done this, what do we have to do? Compile everything. So let's compile everything. And remember that in order to compile, you need to go to this specific directory. Okay, so this is mandatory. We have included this into the commands to prevent errors, but let me remind you about this because this is a typical error for beginners, that they start compiling into a different directory, and then the results, they compile, but then they cannot be found by the ROS system, and there are many strange errors. So we have changed to the proper directory, then done the colcon build for this package, and then finally done the source. You know that you need to do this every time that you compile new packages and so on. Great. So now we can launch the nodes. So first we are going to launch the subscriber. And what we are going to do is to use the Cyclone DDS. We make sure. Then the commands to launch is just this. Okay, so this is just the command to launch it. There is a lot of information here that we have already built. But let me review very quickly. We go to this directory, to the base directory, and in order to do a source. And then we source of the new packages. This is not needed because I just did it, but when we are redoing the commands, sometimes we forget. So that's why we put it here, so you don't have any problem. It's like the educational way of doing this in order to prevent errors for the students. Then the important thing, we are setting the Cyclone DDS, okay, for this test. Cyclone DDS, and then because we set the Cyclone DDS, we stop the daemon, and then we start it again. And then we check, just this is information to be printed on the screen, and then we can see very quickly that everything is correct. Okay, so this is not necessary, but okay, we put it in an educational way. And then finally, we launch our publisher. Okay, so let's go and launch it also here. Right? So now it's starting to publish a lot of things. Let me put it larger, so then it's easier. Okay, so here is publishing and publishing. Now we need to do so this is the publisher. Instead of talker, I'm going to put publisher. So this clarifies the things, and this is going to be the publisher, and what is the name? How did we call it? Subscriber. Yes, subscriber. Okay, instead of listener, subscriber. Good. Then we do the same thing for the Cyclone, for the subscriber. So let me copy all those commands. They are the same. We just prevented the ROS daemon stop and start because it's been already launched on the other terminal. So we don't need to do it here. But all the commands are the same, just launching the subscriber. So let's go. There it goes. So we get this kind of messages, and then given the application that we have built, we can check the total messages lost, which is 0. So we are measuring how many messages we are losing in this communication. And then it looks like in this computer with these conditions, there is no messages that are lost. So everything looks like 0 all the time. Perfect. Excellent. So now this is the thing, okay, the result. But now we are going to do a small test, which is the modification of this variable that we have included into period. This is the period in which the messages are sent. And then it was this period of 0.5 seconds, but now we are going to change into 0 seconds. So it's going to be like as fast as possible of the system. So it's going to be sending messages all the time without waiting for any time. So let's do this change. This is in the publisher, of course, and in the line that is for the init of the time period. Let's go. So I can close this setup because I don't need it to modify the launch also, and then here the publisher. We can get this period, which is in this place. So let's put it into 0. It's in line 25 of the publisher DDS class init function. Okay, so now that we have changed this is a small change, we can Control C the subscriber and Control C the publisher. Okay, and then we need to compile again because we have done a modification. So let me copy the compile, which is, as always, go to the compilation directory, issue the Qualcomm build, and then do a source to make sure that everything is set up with the new values. Okay, so there we go, compilation and source. Great. So now let's launch it again. First, we do the same thing as before for the publisher and check the implementation, the new implementation. Let's go. And launch. There it goes. Okay, there it goes. It's launching everything. And then let's go to the subscriber tab and copy the command and let's see what happens. Okay, here we can see some red things, but it's going so fast that it's going. Let me stop it. Let me Control C and let's go up into the messages. So here it says that a message has been lost here, but then as it goes so fast, it says a lot of messages have been lost. Okay, because here another one has been lost, but as it goes so fast, it's losing a lot of messages in there. Yes, so that can happen because the system cannot manage this. Okay, then the effects, as it says, it could be different based on the computer that you are using, based on many different things. So if you have more cores, maybe there will be very little messages lost. And if your system is lower, then you will get more in performance. So now the idea is that let's change, for example, in order to use the RMW implementation, let's use the fast RTPS now, and let's see what happens. Okay, so let me see what happens. So I'm going to copy, in this case, this is Cyclone, and then we are going to copy into fast RTPS. Okay, so let's copy the command and change it. So first go to the publisher. And then let's go with the other one also, with the subscriber. Okay, so we get some messages also lost. Then by doing this, so I think that the numbers are more or less the same. Yeah, so here is 3,000 and so on. So it looks like a little bit more based on the total amount of time that this has run, but I don't know exactly. But what I wanted to show you is that you can do this kind of tests between the different implementations and measure the differences between one and another, and then do some benchmarking based for your own application of what you need. Okay, so that will be an example of checking different the same program with different RMW implementations. Okay, I'll leave it to you to do a very good comparison between the two and see if one of them is more or less than the other. Let me know on the comments, okay, about what you are getting. Great, and that's it, a basic implementation about these are the very basic concepts about DDS. If you want to know more, a lot more, then please check our course and support our job by getting this and also getting an excellent learning with this course. Say thank you very much for your attention here in this crash course. I hope that you learned a lot, at least as an introduction into ROS, to ROS2, in a very fast way with the main concepts. And then from this point, you can now decide whether to go further, study more, or just because you get enough for your purposes. Maybe it's okay just to get the idea. That is perfect. Then if you want to learn more, consider learning about our courses here at The Construct, because we are the best academy online for learning about this. I hope that everything goes okay for you. See you around the world with many ROS things. Thank you very much. Bye-bye.